Hello and welcome to Sleepy Science. What if the objects around you are not ordinary at all, but hidden physics machines working quietly every second of your life? What if soap is not just cleaning grease, but breaking it apart with molecular tricks? What if bubbles are solving geometry? Ice is floating because water breaks a usual rule of nature. Coffee stains are mapping invisible currents, and dust in sunlight is revealing the secret weather inside your room. In this journey, we'll look again at the things you thought you already understood. Boiling water, steam, towels, cracks, rubber, glue, static clothes, touchscreens, microwaves, refrigerators, fans, mirrors, rainbows, headphones, elevators, airplanes, tires, pressure cookers, popcorn, and the everyday objects shaping your world. These are not random facts. They are real pieces of physics hiding in plain sight, turning your home, your kitchen, your phone, your clothes, and even your own skin into a living museum of forces: heat, pressure, light, electricity, and motion. So before we begin, tell me in the comments, which everyday object do you think is secretly the most mysterious? Tap like if you enjoy seeing ordinary reality become strange. Subscribe for more calm science that makes the familiar world feel unfamiliar again. And now, let's step quietly into the hidden physics of everyday life. Because the deeper you look at ordinary objects, the more you realize they were never ordinary at all. Why soap breaks, grease apart. Beneath every greasy plate, every oily fingerprint, and every slippery trace left on your skin, there is a quiet disagreement happening at the molecular level. Water wants one kind of world, grease wants another, and soap is the strange mediator that makes them face each other. You see the scene every day, so ordinary that it almost disappears from attention. A pan shines with a thin film of oil. Your fingers feel slick after touching butter. A drop of water lands on a greasy surface and refuses to spread properly, pulling itself together as if it would rather stay alone than enter that oily layer. At first, it feels like dirt is simply clinging hard, like grease is stubborn because it is thick or sticky. But the deeper truth is more interesting. Grease does not stay because it is stronger than water. It stays because water cannot easily connect with it. Water molecules are highly attracted to one another, forming a restless, invisible community of tiny charges that constantly pull and rearrange. Grease molecules, by contrast, are mostly non-polar, meaning they do not offer water the same kind of electrical attraction. So when you rinse oily skin with plain water, the water may move across the surface, but it has no good way to grip the oil. It slides past the problem. It touches the boundary and fails to enter. This is why a greasy dish can sit under running water and still feel dirty afterward. The water has motion but not permission. The oil has no reason to surrender. Then soap enters, and the entire situation changes, because soap is built like a tiny double agent. One end of a soap molecule is attracted to water, while the other end avoids water and prefers oily substances. This simple split personality gives soap its power. When you add soap and begin to rub, the oil-loving ends push into the grease, while the water-loving ends remain facing outward toward the water. Slowly, the flat oily film begins to lose its unity. It is surrounded, separated, lifted, and broken into smaller droplets. Soap does not erase grease like a chemical weapon. It reorganizes it. It turns a smooth, clinging layer into tiny packages that water can carry away. These packages are called micelles, and they are one of the quiet masterpieces of everyday chemistry. Inside, the oil-loving parts of the soap hide with the grease. Outside, the water-loving parts face the surrounding water, making the whole structure acceptable to the water around it. In other words, soap gives grease a disguise. It dresses oil in a water-friendly surface, and once that happens, rinsing can finally do what it could not do alone. The grease leaves not because it became water, but because soap built a bridge between two substances that normally reject each other. This is also why rubbing matters. When you scrub your hands or a dish, you are not just helping in a vague way. You are increasing contact. You are breaking the oil layer into smaller regions. You are giving soap molecules more edges to attack, more surface to surround, more chances to lift the grease away from skin, metal, ceramic, or glass. Warm water can help too, not because hot water is magical, but because many fats and oils become softer and less viscous when warmed. A thick, greasy film that resists movement at lower temperature may loosen more easily when heat makes it flow. Still, heat without soap often fails because the basic incompatibility remains. The oil may soften, but water still cannot truly hold it. Soap solves the deeper problem, not hardness, but separation. And there is another detail hidden in the bubbles. People often believe foam is what cleans, because foam is the part they can see. But bubbles are not the main cleaners. Foam is mostly a visible sign that soap is present and air has been trapped in films of soapy water. The most important action happens far below sight, where individual soap molecules gather around grease and dirt. A soap that does not foam much can still clean. A dramatic pile of bubbles can look powerful while doing less than you imagine. The truth is quieter, smaller, and more precise. Cleaning happens at boundaries, at interfaces, at places where substances meet but do not naturally mix. Soap lowers the tension at those boundaries, allowing water to spread better, slip under oily dirt more easily, and pull particles into motion. This is why dish soap can make oil scatter on water, why a greasy fingerprint fades under a soapy wipe, and why washing your hands with soap removes many microbes more effectively than water alone. Not because soap always destroys everything living on your skin, but because many microbes and particles are trapped in oils and films that soap can loosen and rinse away. The act of washing is not just a symbolic ritual of cleanliness, it is a physical relocation. Something that belonged to your surface is persuaded into the water and sent away. And when you notice this, soap begins to feel less like a product and more like a lesson in connection. It does not win by becoming entirely one thing or another. It works because it belongs partly to both worlds. One side understands water, one side understands grease. It is effective because it can stand at the border without being rejected by either side. And maybe that is why such a simple object carries a strangely deep meaning. Many problems in life do not break apart because we push harder. They break apart when we finally understand what is holding them together. Grease clings because it is comfortable with itself and distant from water. Fear clings in similar ways. Old habits cling. Memories cling. Not because they are impossible to move, but because the right bridge has not yet been built. Soap shows you that release is often not destruction. It is translation. It is giving something trapped a path into motion. So the next time you wash a dish, clean your hands, or watch cloudy water spiral down the drain, pause for a moment. You are not only seeing dirt disappear, you are watching billions of tiny structures gather, surround, and carry away what plain water could not touch. You are watching chemistry turn refusal into flow. And in that ordinary sink, under the soft sound of running water, the world is quietly teaching you that even the most stubborn things can let go when the right connection is made. How bubbles choose. Minimal shapes. A bubble looks innocent until you realize it is solving a problem your mind would struggle to calculate. How to hold air inside the smallest possible skin. You see it drift from a wand, trembling in the light, round and weightless, almost childlike. And it feels like decoration, like play, like something too fragile to have a law inside it. But every bubble is a moving answer to a deep physical question. It is made from a thin film of liquid, usually water strengthened by soap, stretched around a pocket of air. That film does not want to be large. The molecules at its surface are pulled inward by their neighbors, creating surface tension, a kind of invisible tightening that makes the film behave like an elastic sheet. Because a larger surface costs more energy, the bubble naturally moves toward the shape that uses the least surface while still enclosing the air inside. And for a free bubble floating in air, that shape is a sphere, not because the bubble knows geometry, not because nature has preferences in the human sense, but because the sphere spreads tension evenly in every direction and gives the most enclosed space for the least surface. If you tried to make a cube-shaped bubble in open air, the corners would not survive, because corners create uneven tension. The film would pull, smooth, and round itself until the extra surface was gone. This is one of the quietest forms of intelligence in nature. Not thought, but tendency. not planning, but energy finding the easiest path downward. A bubble is not choosing like a person chooses. It is choosing the way a river chooses a valley, the way a hanging chain chooses a curve, the way a stretched sheet settles into balance. It is physics becoming shape. And the deeper you look, the more surprising it becomes, because bubbles do not only form spheres. When they touch other bubbles, their perfect roundness changes. A cluster of bubbles becomes a negotiation. Each bubble still tries to reduce its surface, but now it must share walls with its neighbors. The film between two bubbles becomes flat or gently curved, depending on the pressure inside each one. A smaller bubble usually has higher internal pressure than a larger one because tighter curvature creates stronger pressure inside. That is why tiny bubbles can shrink and vanish into larger ones over time in foams. Air slowly diffuses from high-pressure small bubbles into lower-pressure larger bubbles. Even in a sink full of foam, there is a hidden economy of pressure and surface area unfolding silently. The bubbles are not random. Their walls meet in very specific ways. When three soap films meet along a line, they tend to meet at equal angles because that balances the pulling forces. When several of those lines meet, they form stable junctions that also obey strict geometric rules. Scientists call these patterns Plateau's laws, named after the physicist Joseph Plateau, who studied the shapes of soap films in the 19th century. But you do not need formal mathematics to feel the wonder of it. Dip a wire frame into soapy water and pull it out, and the film will stretch across the frame in a shape that often looks impossible, almost architectural. It may curve inward like a saddle, twist through open space, or split into delicate surfaces that meet cleanly, as if an invisible sculptor arranged them. What you are seeing is a minimal surface, a form that reduces area while obeying the boundaries you gave it. Change the frame and the answer changes. The film is not seeking beauty, yet beauty appears because balance often looks beautiful to the human eye. It is the same reason honeycomb patterns, cracked mud, and the veins in leaves can feel strangely meaningful. Nature often arrives at elegance by removing waste, but a bubble is also a reminder that minimal does not mean simple. The sphere may be simple, but the forces behind it are subtle. The film has two surfaces, an outer surface touching the air outside, and an inner surface touching the air inside. The liquid between them is extremely thin, sometimes thinner than a human hair by many thousands of times. Gravity pulls the liquid downward, evaporation thins the film, air currents disturb it, and tiny vibrations ripple through it. That is why bubbles shimmer, wobble, and finally pop. They are temporary agreements between forces that never stop moving. The colors you see on a bubble are not painted onto it. They come from light reflecting from the front and back of the thin film, overlapping in ways that strengthen some colors and weaken others. As the film drains and changes thickness, the colors slide and swirl, quietly revealing the bubble's own fragility. In a way, the bubble shows you its approaching death through color. When the film becomes too thin or a speck of dust breaks its surface, the tension that once held everything together suddenly pulls the film apart, and the bubble disappears almost instantly. Not slowly, not dramatically, but with a tiny collapse of order. And yet, for the few seconds it existed, it was a perfect demonstration of how the universe often works. Forces pull, matter responds, shapes emerge. There is no need for instruction from outside. The rules are already inside the material. This is what makes bubbles so powerful as a lesson. They teach that form is not always imposed. Sometimes form is discovered by letting tension settle. They teach that beauty can be a side effect of efficiency. They teach that even something fragile can reveal a law strong enough to shape planets, droplets, cells, and foams. When you watch a bubble float across a room, you are watching air wrapped in a liquid boundary, held together by molecular attraction, rounded by surface tension, colored by light interference, and slowly undone by drainage, evaporation, and disturbance. It is not empty play. It is a small universe with a skin. And perhaps that is why bubbles feel so haunting if you look at them long enough. They are almost nothing, yet they obey deep laws. They last only moments, yet in those moments, they become the most efficient container they can be. They do not fight their fragility. they become beautiful inside it. And when they vanish, they leave behind a quiet question. How much of what we call beauty is simply balance made visible? And how many things in your own life are still trying, silently, to find their smallest, calmest, most natural shape? Why ice floats on water? The strangest thing about ice is that it breaks one of the quiet rules your intuition expects from the world. When water becomes solid, it does not sink into itself, but rises. You see an ice cube floating in a glass and barely notice it, because the scene feels familiar, harmless, almost too ordinary to question. But if most substances behaved like water, that cube should fall. In many materials, cooling makes molecules slow down, move closer together, and pack more tightly, so the solid form becomes denser than the liquid form. But water does something rare. As it freezes, its molecules arrange themselves into an open crystal structure, held by hydrogen bonds that create extra space between them. Liquid water is more crowded and restless, with molecules constantly slipping, rotating, and reconnecting. Ice, by contrast, becomes more orderly but also more spacious. It is like a crowd that, instead of squeezing together when told to stand still, steps into a careful pattern with empty gaps between every person. Those gaps make ice less dense than liquid water, and because it is less dense, it floats. This is not just a small curiosity of the kitchen. It is one of the reasons life on Earth survived long enough for you to exist. If ice sank, lakes and ponds in winter would freeze from the bottom upward. Each new layer of ice would drop, exposing more water to the cold, and over time, many bodies of water could freeze much more completely. Instead, ice forms on the surface, floats there, and becomes a kind of cold shield. It insulates the liquid water beneath it, slowing further heat loss and creating a hidden refuge where fish, plants, microbes, and whole ecosystems can remain alive below the frozen skin. Beneath a winter lake, life continues in dim stillness because ice stays above, not below. Water has another unusual habit connected to this. It becomes densest not at freezing, but around 4 degrees Celsius. As surface water cools toward that temperature, it sinks, helping mix lakes. But once it gets colder than that, it begins to expand slightly and stays closer to the top, where it can freeze. This strange behavior shapes seasons inside lakes, affects oxygen movement, influences aquatic life, and turns freezing from a total collapse into a layered balance. And when you hold an ice cube, you are holding a small piece of that same planetary logic. The cube floats because its solid structure has more volume than the liquid that formed it. That is also why water can burst pipes when it freezes. It expands with enormous pressure, not because it becomes explosive, but because the forming crystal network demands more space. If that space is trapped inside metal, stone, or plastic, the pressure can break the container. The same expansion helps crack rocks in cold climates. Water seeps into tiny fractures, freezes, expands, and slowly pries the stone apart. A force so gentle as rain can become a sculptor when cold gives it a crystal body. Mountains crumble grain by grain. Roads split, soil shifts, buildings strain, all because frozen water refuses to occupy less space. The floating ice in your drink is connected to glaciers, frost heave, frozen lakes, broken cliffs, and the deep architecture of landscapes. Yet the deeper beauty is molecular. Each water molecule has a shape and an uneven distribution of electric charge, so it can attract nearby water molecules in directional ways. These attractions are called hydrogen bonds. They are not as strong as the bonds holding each water molecule together, but they are strong enough to guide how water organizes itself. In liquid water, these bonds constantly form and break, a flickering network that changes at unimaginable speed. In ice, the network becomes more stable and geometric, locking molecules into a pattern that preserves distance. That pattern creates the open structure that lets ice float. So the real answer is not simply ice is lighter than water. That is true, but it hides the wonder. Ice floats because water's molecules, when cold enough, choose order over closeness. They become stable by leaving space, And that idea feels almost philosophical when you let it settle. Stability does not always mean compression. Sometimes a thing becomes stronger by opening. Sometimes structure requires emptiness. The frozen surface of a lake is not just a layer of cold matter. It is an arrangement of tiny angles and attractions, a fragile architecture keeping an underwater world from becoming a tomb. Even the whiteness of snow and ice tells part of the story. Pure ice can be clear, but snow looks white because countless tiny ice crystals scatter light in many directions, sending a mixture of colors back to your eyes. The same substance can appear transparent, blue, white, solid, flowing, deadly, protective, delicate, and powerful, depending on how it is arranged. That is the quiet lesson water keeps teaching. Matter is not only what it is made of, but how it is organized. A liquid becomes a floating solid because invisible geometry changes the space between molecules. A winter lake becomes survivable because density reverses expectation. A planet becomes habitable because a common substance has uncommon behavior. So the next time you hear ice crack in a glass, or see a frozen pond holding itself above dark water, do not pass over it too quickly. You are looking at an exception that became a foundation. You are seeing a rule broken in just the right way, and beneath that floating ice, whether in a cup or across a silent lake, the universe is whispering something simple and profound. Sometimes what rises is not lighter because it is empty, but because its hidden structure has learned how to hold space. The physics of boiling. A pot of water does not begin to boil because heat suddenly appears inside it, but because the liquid is finally losing a long, invisible argument with pressure. At first, nothing dramatic seems to happen. You place the pot on the stove, the metal warms, and the water sits there looking almost unchanged, as if it is refusing to reveal the violence building underneath. But at the molecular level, the calm surface is misleading. Every water molecule is already moving, bumping, rotating, pulling away, being pulled back, trading energy with its neighbors in a restless, invisible crowd. Heating does not add bubbles to water. Heating increases the motion of that crowd. The molecules near the bottom, closest to the hot metal, gain energy first. Some move faster, some collide harder, and more of them become capable of escaping the liquid state. This escape can happen quietly from the surface at almost any temperature, which is why a wet towel dries even in a cool room. That is evaporation. Individual molecules leaving from the surface when they have enough energy to break free. Boiling is different. Boiling is when escape begins inside the liquid itself. It is not just water leaving from the top. It is vapor forming within the body of the water, rising upward in pockets. But for that to happen, those vapor pockets must be strong enough to survive being squeezed by the surrounding water and the air above it. This is why pressure matters. The atmosphere is pressing down on the water all the time, even when you cannot feel it. At sea level, water usually boils around 100 degrees Celsius because at that temperature, its vapor pressure becomes strong enough to match the outside pressure pressing against it. In simpler terms, the vapor inside the water can finally push back hard enough to exist as bubbles. If you climb a mountain, the air pressure is lower, so water does not need to get as hot before its vapor can push back. It boils at a lower temperature. That is why cooking can take longer at high altitude. The water may be boiling loudly, but it is not as hot as boiling water near sea level. And this already reveals one of boiling's hidden lessons. The sound and motion of a process do not always tell you how much energy it carries. A pot can rage and still be cooler than you assume. As the water warms, you may first see tiny bubbles clinging to the sides or bottom of the pot. Many of those early bubbles are not yet true boiling. They can be dissolved gases leaving the water as it heats, because warm water holds less dissolved gas than cold water. Then, as the bottom grows hotter, small pockets of water vapor begin forming at rough spots on the metal or tiny imperfections in the surface. These places are called nucleation sites, and they matter because bubbles do not easily appear in perfectly smooth liquid. A new bubble needs a starting point, a tiny shelter where vapor can gather before the surrounding liquid crushes it. This is why bubbles often begin at the bottom of the pot, not randomly in the middle. The pot itself is helping the water change state by offering little cracks, scratches, and rough places where vapor can be born. As heating continues, those bubbles grow, detach, rise, and sometimes collapse before they reach the surface if they pass into cooler layers above. That is why simmering begins before full boiling. You are watching vapor attempt to survive the journey upward. Eventually, the whole liquid becomes hot enough that the bubbles rise through it without disappearing. They burst at the surface, releasing water vapor into the air, and the pot enters a rolling boil. But here is the part that feels almost unnatural. Once water is boiling steadily, adding more heat does not make the liquid temperature climb much higher under the same pressure. The extra energy mostly goes into changing liquid water into vapor. It is being spent on transformation, not temperature. The thermometer may stay near the boiling point while the stove continues pouring energy in. The water is absorbing heat, but instead of becoming hotter, it is breaking the attractions that hold its molecules together as a liquid. This hidden energy is called latent heat, and it is one reason phase changes are so powerful. The water looks like it is simply bubbling, but what you are seeing is energy being used to rearrange existence itself, turning a dense liquid into an expanding gas. The molecules are not becoming different chemicals. They are still water, but their relationship to one another has changed. In liquid, they remain close, constantly attracting and releasing one another. In vapor, they are much farther apart, moving freely, occupying far more space. That sudden expansion is why boiling can shake a lid, why steam pushes upward, why kettles whistle, and why engines throughout history learn to turn heated water into mechanical force. Boiling is not just a kitchen event. It is one of the great transitions of matter, a threshold where hidden motion becomes visible. The bubbles are not decorations. They are evidence of a boundary being crossed. And yet boiling can also be strangely deceptive. A perfectly clean, smooth container can sometimes let water become superheated, meaning the water rises above its normal boiling temperature without forming bubbles, because there are too few nucleation sites. Then, if disturbed, it can erupt suddenly as vapor forms all at once. This is why heating water in a microwave can occasionally be dangerous, especially in very smooth cups. The water may appear calm while holding more energy than its surface admits. One small movement, one spoon, one grain of powder, and the delayed boiling can burst upward. It is a rare everyday reminder that stillness is not always safety. Sometimes the absence of visible change only means the system has not yet found the place where change can begin. In a normal pot, however, boiling becomes a rhythm. Heat enters from below, vapor forms at rough points, bubbles rise, the surface breaks, vapor escapes, and the liquid slowly vanishes into the air. If you keep boiling long enough, the pot empties not because the water was destroyed, but because it crossed from a visible, touchable form into an invisible one. The same substance left the container by becoming harder to see. And this is where boiling becomes more than a physical process. It teaches that transformation is often not a single dramatic moment, but a threshold reached after countless tiny motions. Long before the first large bubble rises, the molecules have been preparing. Long before the surface breaks, energy has been gathering. The visible event is only the final announcement of an invisible change. So the next time you watch water boil, do not see only a pot on a stove. See pressure holding the liquid down. See heat stirring motion from beneath. See vapor searching for birthplaces in scratches too small for your eyes. See bubbles as temporary rooms of gas rising through a collapsing world of liquid. See energy being spent not merely to warm, but to free. And maybe, as the steam lifts and disappears, you will feel the quiet question hidden inside this ordinary scene. How many things in life seem unchanged only because their boiling point has not yet been reached? And how much invisible motion is already happening beneath the surface before anything finally rises? Why steam burns more than hot water? The most dangerous part of steam is that it looks almost weightless. Yet when it touches your skin, it can deliver a hidden second wave of heat that boiling water has already spent. You may think of a burn as something simple. The hotter substance hurts more, the cooler one hurts less. But steam breaks that intuition because the damage is not only about temperature, it is also about how much energy the substance can hand over when it meets you. Imagine two forms of water at roughly the same temperature near boiling. Liquid water in a kettle and steam rising from it. They may share a similar temperature, but they do not carry that heat in the same way. Hot water can transfer heat into your skin as it touches you, and that is already dangerous. But steam arrives as water vapor, a gas that was created only after the liquid absorbed a large amount of extra energy to separate its molecules and lift them into the vapor state. That energy is hidden in the steam, not visible as a higher temperature, but stored in the fact that it has changed form. Then the steam touches your cooler skin. In that instant, it begins to condense back into liquid water. And when it condenses, it releases that stored energy directly onto the surface it touches. This is why steam can burn more severely than liquid water at the same temperature. It does not just cool down against your skin, it changes phase on your skin, and that phase change gives back a large amount of heat. It is like someone arriving at your door carrying not only the heat you can see, but also a sealed package of invisible energy that opens the moment it lands. That is the brutal elegance of condensation. The steam becomes water again, and in doing so, it pays back the energy it once borrowed to become vapor. Your skin receives that payment, and because skin is made of water-rich tissue, it is very vulnerable to this kind of heat transfer. Proteins begin to change shape, cells are damaged, and the injury can deepen quickly if the contact continues. There is another reason steam is so deceptive. As a gas, it can move in ways liquid water cannot. A splash of hot water may hit one area and roll away, depending on angle, clothing, and movement. Steam can flow around curves, rise into sleeves, enter small spaces, wrap around fingers, and reach into folds of skin. It does not need to fall like a liquid. It drifts, expands, and surrounds. Then, wherever it meets a cooler surface, it condenses and releases heat. This is why a cloud from a kettle spout, a pressure cooker vent, or a burst pipe can be so dangerous even if it appears soft or ghost-like. The whiteness you often see above a kettle is not pure, invisible steam itself, but tiny droplets that have already condensed in the cooler air. True water vapor is invisible. That detail matters because it teaches you something unsettling. The part you can see is not always the whole threat. The invisible region closest to the source may be extremely hot vapor before it becomes the visible mist. So when people wave a hand through just steam, they may be reaching into a moving boundary between gas and liquid, between stored energy and released energy. And steam does not need to look violent to be powerful. Its danger comes from intimacy. It gives up its energy exactly where it condenses. Hot air, for example, usually burns less severely than steam at the same temperature because air holds and transfers much less heat. You can briefly place your hand in a hot oven without the same immediate injury you would get from touching boiling water, though both can burn you. The difference is not only temperature, it is heat capacity and heat transfer. Water is exceptionally good at carrying heat, and steam adds the phase change effect on top of that. When steam becomes liquid on your skin, the newly formed hot water can remain there for a moment, continuing to transfer heat even after condensation. So the injury can be layered. First, the vapor releases hidden energy. Then the hot condensate stays in contact. Then the tissue continues absorbing heat. This is why steam burns can feel sudden and deep, as if something gentle turned violent without warning. The same principle is used in reverse in many useful technologies. Steam heating works well because condensation releases a lot of energy efficiently. Old radiators, industrial systems, and steam cooking all rely on the same property that makes steam dangerous. When steam condenses on a cooler surface, it gives up heat powerfully. In a kitchen, that can cook food quickly. In a machine, it can transfer energy. On skin, it can injure. The physics does not change its character depending on whether we call it useful or harmful. It simply obeys the rules of energy, moving from one place to another. And this is what makes steam such a strange teacher. It reminds you that danger does not always announce itself with weight, color, or hardness. Some of the most powerful things in the world arrive as vapor, pressure, heat, absence, silence. They do not look solid enough to matter, yet they can change matter the moment they touch it. Steam is water in a temporary state of escape, carrying the memory of the energy that freed it from liquid form. When it meets your cooler skin, that escape ends, and the borrowed energy returns. So the next time you lift a lid from a pot or open something that has been sealed under heat, pause before leaning close. What rises may look delicate, almost harmless, like a breath from the food itself, but inside that pale movement is a hidden transaction. Vapor becoming liquid, stored energy becoming contact, softness becoming injury. And beneath that everyday warning is a deeper question worth carrying with you. How many things in life seem harmless only because their force is hidden, waiting for the exact surface where it can finally be released? Surface tension in a water drop. A single water drop is not just a tiny piece of liquid. It is a small world holding itself together against the air, quietly pulling its own surface into a shape that reveals an invisible force. You have seen it countless times. A bead of rain resting on a leaf, a drop trembling at the edge of a faucet, a round pearl of water sitting on a waxed car, refusing to spread as if the surface beneath it has been rejected. It looks soft, almost powerless, but if you could shrink yourself down to its edge, you would find a border under tension, a place where molecules are being pulled inward with remarkable discipline. Inside the drop, water molecules are surrounded by other water molecules on every side, tugging on each other in all directions. The pulls mostly balance, but at the surface, the molecules do not have water above them, only air, so they are pulled more strongly inward and sideways by the molecules beneath and beside them. This creates surface tension, the reason a drop behaves as if it has a delicate elastic skin. It is not really a skin in the way your skin is a layer of tissue. It is a collective effect, a boundary created by attraction. The surface tries to shrink because exposed surface costs energy, and the drop settles into a shape that keeps that exposed area as small as possible for the amount of water it contains. That is why small drops tend to become round. The roundness is not decoration. It is physics smoothing the liquid into a quieter state. But the shape of a water drop is never controlled by surface tension alone. Gravity pulls it downward. The surface beneath it may attract or repel it. Dust, temperature, vibration, and motion all interfere. A tiny drop can look almost perfectly spherical because surface tension dominates its small weight. A larger drop begins to flatten or sag because gravity becomes harder to ignore. This is why raindrops are not actually shaped like the cartoon tear falling from the sky. Small raindrops are close to round. Larger ones flatten at the bottom as they fall, pushed by air resistance, and very large ones can become unstable and break apart. The familiar teardrop shape belongs more to imagination than to falling rain. Real droplets are negotiations, not symbols. They are shaped by forces arguing in silence. Place water on clean glass and it spreads more because the glass attracts the water strongly. Place it on a waxy leaf and it beads up because the water is more attracted to itself than to the surface. This difference is described by how much the droplet wets the material. But you can understand it without heavy terminology. If the surface welcomes water, the drop flattens. If the surface refuses it, the drop curls inward and holds itself high. This is why lotus leaves stay so clean. Their surfaces are not just waxy. They are also covered in tiny textures that reduce contact with water. Drops roll off, picking up dirt as they move. Nature turned surface tension into a cleaning system long before humans studied it in laboratories. The same effect appears on rain jackets, treated windshields, and waterproof fabrics, where water gathers into beads instead of soaking through. A droplet is teaching you that contact is not simple. Touching a surface does not mean belonging to it. Sometimes the smallest distance, the faintest mismatch in attraction, changes whether something spreads, clings, or rolls away. Surface tension also explains why certain small creatures can stand or move on water without sinking. A water strider does not float because it is weightless. It survives because its long, water-repelling legs spread its weight gently over the surface without breaking it. The water bends under the legs like a stretched film, and the insect stands on that deformation. If the surface is weakened, the trick fails. A tiny needle can also rest on water if placed carefully, not because metal is lighter than water, but because the surface can support it when the force is spread and the boundary is not pierced. The moment the surface breaks, the illusion ends. And that word, illusion, matters here because water often looks passive. It takes the shape of a cup, flows down slopes, slips through fingers. Yet at the smallest scales, water is full of structure and preference. It clings to itself. It resists being pulled apart. It gathers into beads, stretches into thin films, holds droplets on spider webs, forms dew on morning grass, and hangs from a faucet until the weight becomes too much. When a drop finally falls from a tap, there is a dramatic moment hidden inside the ordinary. The drop grows as more water arrives. Surface tension holds it to the faucet, pulling upward around the neck of liquid. Gravity pulls downward. For a while, the drop survives as a hanging body, stretched between attachment and release. Then the neck thins, the balance fails, and the drop detaches. Even then, it does not fall as a shapeless blob. It contracts and rounds itself in mid-air, sometimes leaving behind a smaller satellite droplet, a tiny echo of the break. High-speed cameras reveal this as a graceful sequence of stretching, thinning, snapping, and recoiling. To the naked eye, it is only a drip. To physics, it is a miniature drama of failure and recovery. Surface tension is also why droplets can merge so suddenly. Two drops sitting close together may remain separate until their surfaces touch. Then the boundary between them vanishes, and the two become one, pulling themselves into a new shape. The motion can be surprisingly fast, because once the separating surface disappears, the liquid reduces its exposed area by joining. You see it when rain streaks combine on a window, when sweat beads merge on skin, when morning dew gathers into larger drops before sliding from a blade of grass. A drop is always trying to reduce unnecessary surface, and merging is one way it does that. But there is a deeper lesson in the way a droplet lives. It is held together not by a shell, not by a wall, not by hardness, but by relationship. Every molecule participates in a shared attraction, and from that countless tiny pulls create a visible form. No single molecule decides the shape. The shape emerges from all of them acting together. That is why a water drop can feel strangely alive when you really look at it. It trembles, resists, gathers, releases, joins, separates, reflects the world upside down on its curved surface, and then vanishes into flow. It is both fragile and organized. It has no solid boundary, yet it has identity. And maybe that is why watching a drop can become more than watching water. It asks you to reconsider what holds things together. Not everything needs a hard edge to have form. Not everything that is soft is weak. Sometimes coherence comes from countless quiet attractions, each too small to impress you alone, but together strong enough to shape the visible world. So the next time a raindrop rests on a window or a bead of water clings to your fingertip, do not see only moisture. See a surface pulling itself inward. See gravity waiting patiently below it. See the material beneath either welcoming it or turning it away. See a tiny boundary where air, water, and attraction meet. And then ask yourself how many ordinary things around you are held together in the same way. Not by force you can see, but by invisible relationships, quietly shaping the world into something that can stay whole for just a little while. Capillary action in towels and plants. Water is supposed to fall, yet inside a towel, a stem, or a hidden vein in a leaf, it quietly climbs. That is the first strange truth behind capillary action. It is the physics of liquid moving through narrow spaces, as if gravity has lost some of its authority. You have seen it happen without thinking about it. A corner of a paper towel touches spilled water, and the wetness begins to crawl upward and outward, darkening the fibers ahead of your hand. A dry cloth meets a drop on the table, and the liquid vanishes into it. Not because the cloth drinks like a living thing, but because its threads contain countless tiny passages where water can pull itself forward. A plant stands in soil, silent and still, and somehow water absorbed near its roots can end up high in its leaves, lifted through thin internal tubes, without any tiny pump beating inside the trunk. It feels almost impossible when you slow down and look at it. How can water rise? How can a towel pull liquid sideways? How can a tree move moisture upward against its own weight? The answer begins with a simple relationship. Water is attracted not only to itself, but also to certain surfaces. When water meets a material like clean glass, paper, cotton, or the inner walls of plant vessels, its molecules can be drawn toward that surface. This attraction is called adhesion. At the same time, water molecules also cling to one another through cohesion. So when some water molecules start to move along a surface, they tug neighboring water molecules with them. In a wide container, this effect is too small to lift much water. But in a very narrow space, the walls are close enough to influence a large portion of the liquid. The water wets the walls, curves upward at the edges, and the pull along the surface helps draw more liquid behind it. The narrower the passage, the more noticeable the rise can become, because the surface has more control compared with the amount of water being lifted. This is why water can climb higher in a thin glass tube than in a wider one, and why a towel, which is really a tangled landscape of tiny gaps between fibers, can spread moisture so effectively. It is not simply absorbing water like a sponge-shaped hole filling up. It is guiding water through microscopic corridors. Each fiber becomes a wall. Each gap becomes a channel. Each channel invites the water forward. Cotton towels work well, partly because cotton is made mostly of cellulose, a material with chemical groups that attract water. The fibers are also twisted, looped, and woven in ways that create many small spaces. When a towel touches liquid, water begins wetting the fibers and moving through those spaces. The motion may look like the towel is greedily pulling water in, but what you are watching is a chain reaction of attraction and geometry. A smooth plastic sheet cannot do this in the same way because water may not wet it well, and there may be fewer useful pathways. A microfiber cloth can behave differently again because its extremely fine synthetic fibers create huge amounts of surface area and tiny gaps, giving liquid many routes to travel. The material matters. The spacing matters. The shape of the hidden passages matters. Even cleanliness matters, because oils or residues on fibers can make water less willing to spread. This is why an old towel, a new towel, a paper towel, and a polished surface do not treat the same spill the same way. Each one offers water a different map. Plants use a deeper version of this same principle, but they combine it with other forces in a living system. Water enters roots from the surrounding soil and moves into narrow tubes called xylem, which run upward through stems, trunks, and leaves. Capillary action helps water rise in these narrow pathways because the water is attracted to the vessel walls and to itself. But in tall plants, and especially trees, capillary action alone is not enough to explain the full climb. The major lifting force comes from transpiration. Water evaporates from tiny openings in leaves, and as it leaves, it pulls on the continuous column of water behind it. Because water molecules cling together, that pull can travel downward through the xylem, drawing more water upward from the roots. It is as if the leaf, by losing water to the air, creates a gentle upward tension through the plant's entire body. The plant does not lift water like a bucket on a rope. It maintains a continuous thread of liquid under pull. That thread can be fragile. If air bubbles enter the xylem, they can break the connection, causing a blockage called an embolism, which makes it harder for water to move. So the life of a plant depends on maintaining invisible continuity, a liquid chain stretching from soil to sky. And this makes every green leaf more extraordinary than it appears. A tree is not only standing there, it is managing water pressure, evaporation, narrow vessels, root intake, and atmospheric demand in a slow, silent exchange with the air. On a hot, dry day, leaves can lose water faster, increasing the pull upward, but if too much is lost, the plant may close its stomata to conserve moisture, slowing the intake of carbon dioxide needed for photosynthesis. So the same openings that allow a plant to breathe also risk drying it out. Life becomes a negotiation between thirst and hunger, between drawing water from darkness and releasing vapor into light. And the connection to a towel is not a joke or a simplification. It is a reminder that the same physical principles can appear in humble and majestic forms. A paper towel spreading a spill across a kitchen counter and a plant drawing water toward its leaves are both using narrow pathways, wettable surfaces, and the tendency of water molecules to pull together. One dries your table, the other helps keep forests alive. The difference is scale, structure, and purpose. The physics is shared. This is what makes capillary action so quietly beautiful. It shows that motion does not always require engines, muscles, or visible force. Sometimes movement begins because a surface invites, a narrow space guides, and a chain of molecules follows. Water does not need to be commanded upward. Give it the right passage, and it will climb as far as the balance of forces allows. Give it fibers, and it will wick. Give it roots, xylem, and leaves, and it becomes part of a living circulation that links underground darkness to sunlight. So the next time you press a towel onto spilled water, or watch a plant recover after being watered, do not see only cleaning or gardening. See a hidden architecture of tiny channels. See liquid responding to surfaces you cannot see. See the same water that falls as rain learning, for a moment, how to rise. And then ask yourself how much of the world moves this way. Not through loud force, not through obvious power, but through small attractions repeated billions of times until they become something that looks almost like intention. Why coffee leaves ring patterns. A coffee stain is not just a dirty circle on the table. It is the fossil of a tiny current system that lived, moved, carried particles, and died while you were not paying attention. You see it after the cup is lifted, a brown ring left behind like a quiet accusation, darker at the edge and paler in the center, and it feels so familiar that it barely seems worth explaining. But that ring is one of the most elegant little clues in everyday physics, because it reveals that drying is not passive. A drop of coffee does not simply sit there and vanish evenly into the air. It contains water, dissolved compounds, oils, and countless microscopic particles from the coffee itself. And as the liquid evaporates, those particles are moved around by hidden flows inside the drop. At first, the drop lands and spreads until its outer edge reaches a position where it gets stuck. This sticking is called pinning. The edge may catch on tiny roughness in the table, microscopic dust, scratches, fibers, or chemical patches on the surface. Even if the table looks smooth to you, to a droplet it can be a landscape full of obstacles. Once the edge is pinned, the drop cannot easily shrink inward as it dries. Its footprint stays almost the same size for a while, like a tent whose outer stakes have been fixed into the ground. But evaporation is still happening, and it does not happen equally everywhere. The outer rim of the drop is thin and exposed, so water molecules near that edge escape into the air more easily than molecules in the thicker middle. The edge is losing liquid faster. Now the drop faces a problem. If the edge keeps evaporating, but the edge cannot move inward, liquid from the center must flow outward to replace what is being lost. This creates a slow internal current from the middle of the drop toward the rim. You cannot see it directly with your eyes, but it is there, quietly dragging suspended coffee particles outward. As the water disappears, those particles are deposited at the pinned edge, where they accumulate into the dark outline you recognize as a coffee ring. The stain is not darker at the edge because the edge was dirtier at the beginning. It becomes darker because the drop's own drying process transports material there. The ring is a record of movement. It is the final map of where the particles were carried before the liquid that moved them vanished. And this makes the coffee ring effect far more than a kitchen curiosity. Scientists study it because the same process appears in paints, inks, blood droplets, medical testing, printed electronics, coatings, and any situation where tiny particles are left behind by an evaporating liquid. If you are trying to print a smooth layer of material, the coffee ring effect can ruin the result by dragging valuable particles to the edges instead of leaving them evenly spread. If you are analyzing dried biological samples, the pattern can influence what you think you see. A tiny stain can become a problem of engineering, chemistry, and design. The humble coffee mark on your desk is connected to technologies that require microscopic precision. What seems like a nuisance is actually a warning from physics. When liquid disappears, the things it carries do not simply stay where they began. They follow the flow, and the flow is shaped by the edge, by the surface, by evaporation, by the temperature of the room, by the shape of the particles, and even by what is dissolved in the liquid. Change any of these, and the final stain can change. If the edge is not strongly pinned, the drop may shrink as it dries, leaving a different mark. If evaporation is slower or more uniform, the outward current may weaken. If the liquid contains substances that change how tension varies across the surface, other flows can appear, sometimes circulating inside the drop and pushing particles away from the edge. This is often called Marangoni flow, and it happens when differences in surface tension create motion along the liquid surface. In some liquids, this internal circulation can fight against the outward coffee ring flow and produce a more even deposit. That is why not every drying drop leaves the same kind of ring. Wine, paint, salty water, tea, blood, ink, and coffee can all dry into different patterns because each liquid carries its own mixture of particles, molecules, and surface behaviors. Even the shape of the suspended particles matters. Round particles often move easily toward the edge and stack there. But elongated or irregular particles can interfere with each other, forming loose networks that resist being swept completely outward. This means the final pattern is not only about the liquid, it is also about the tiny solids inside it, their shapes, their interactions, and how they crowd together as the water leaves. A coffee ring, then, is a small crowd control problem played out in silence. The particles are passengers. The drying liquid is the road system. The pinned rim is the city wall where traffic piles up. And when the water is gone, all you see is the jam it left behind. There is also a strange time story hidden in the stain. While the drop is wet, it is alive with motion. The flows are active, the particles are traveling, the edge is gathering material, the surface is slowly changing shape. But once dry, the whole event is frozen into a pattern. The ring is the memory of a process you missed. It is like seeing footprints after an invisible animal has passed through the room. You did not watch the current, but the deposit proves it existed. And that is what makes these patterns so quietly powerful. They remind you that the world leaves traces of forces that were never visible while they were acting. The table does not show you evaporation molecule by molecule. The coffee does not announce that its particles are being pulled outward. The edge does not glow when it pins the drop in place. Yet the final mark contains the entire story. Where the boundary held, where the water escaped fastest, where the internal current flowed, where the particles came to rest. A stain becomes a document, a circle becomes evidence, and maybe this is why the coffee ring feels more interesting the longer you think about it. It is not random dirt, it is order produced by disappearance. The liquid leaves, and in leaving, it organizes what remains. There is something almost unsettling in that, because many things in life work the same way. You often notice the pattern only after the motion is over. You see the residue of choices, the outlines of habits, the darker edges where attention kept returning, and only later do you realize that invisible currents were carrying pieces of you there all along. So the next time your cup leaves a brown ring behind, do not wipe it away too quickly in your mind. Look at it for a second. It is a tiny physics experiment completed without permission. It is evaporation made visible through particles. It is a reminder that even a quiet drop can contain a hidden circulation, and that sometimes the most ordinary marks are not stains at all, but maps of movement after the moving has disappeared, the hidden math of cracks. A crack is not a line of damage. It is a decision made by matter under pressure, a sudden route chosen through a hidden landscape of weakness. You see a crack in a phone screen, a wall, a dried field, a ceramic cup, and your mind reads it as failure, as something broken and therefore simple. But a crack is not simple. It is one of the most precise ways the physical world reveals where stress has been living in silence. Before the crack appears, the object may look whole, the glass may shine, the plate may feel solid, the concrete may seem calm, but inside, forces are already being stored, redirected, concentrated around tiny flaws too small for your eyes to notice. No material is perfectly smooth or perfectly uniform. Even the clearest glass contains microscopic scratches, invisible dents, small variations, impurities, and internal tensions left from cooling, shaping, or impact. Most of the time, these flaws do nothing. They sleep inside the object like unopened doors. But when stress arrives, one of those flaws can become a starting point. The strange thing is that the force does not spread evenly around a crack or scratch. It gathers at the sharp tip. A crack tip is like a whispering point where pressure becomes focused, where the material is asked a brutal question. Can you keep holding together here? The sharper the flaw, the more intensely stress can gather there. This is why a tiny scratch on glass can matter more than a shallow smooth mark that looks larger. Sharpness is dangerous because it gives stress a place to concentrate. Once the material at that point can no longer resist, bonds between atoms or grains begin to separate, and the crack moves forward. It does not move randomly. It follows a path shaped by the stress around it, the structure of the material, the energy available, and the obstacles it meets. In brittle materials like glass, dry ceramic, or some stones, there is little ability to bend or stretch around the damage, so the crack can shoot forward suddenly, sometimes faster than your eye can follow. In tougher materials, the story changes. Metals, wood, skin, bone, and many composites can absorb energy in more complex ways. They may deform, tear slowly, stretch fibers, redirect the crack, blunt the crack tip, or force the fracture to take a longer path. This is why toughness is not the same as hardness. A hard object resists being scratched or dented, but it may still shatter easily if it cannot absorb energy. A tough object may be less hard, but better at stopping cracks from racing through it. Think of a ceramic mug and a rubber sole. The mug is hard, but if dropped, it may break. The rubber is softer, yet it survives impact because it can deform and spread the energy. The hidden math of cracks is really the hidden accounting of energy. For a crack to grow, the material must spend energy creating new surfaces. When a solid splits, it produces two fresh faces where there used to be one continuous body. That costs energy. A crack advances when the energy released by relaxing the stressed material is greater than the energy needed to create those new surfaces. You do not need equations to feel the meaning of this. The crack grows only when breaking becomes the easier way for the object to relieve what it has been carrying. That is why fracture can feel almost emotional when used as a metaphor. But the physics is real. Stress accumulates, resistance holds, then one path opens and the stored tension escapes through it. You can see this in a windshield after a small stone strike. At first there may be only a tiny star-shaped chip, but that chip contains sharp tips. Temperature changes, vibration or pressure can make one line lengthen. It creeps, pauses, turns, then continues, because the stress field changes as the crack grows. Modern laminated windshields are designed to keep the glass from flying apart, using a plastic layer between glass sheets to hold fragments and slow disaster. Engineering is often the art of giving cracks a harder life. Airplane windows are rounded instead of square because sharp corners concentrate stress. Bridges and ships are inspected for fatigue cracks because repeated loading can slowly grow flaws over time, even when each individual force seems safe. A paperclip bent once may survive. Bend it again and again, and microscopic damage accumulates until it snaps. The break feels sudden, but the history was written earlier. Cracks often have memory. They remember every cycle of strain, every hidden defect, every old impact, every temperature shift. And the patterns they create can be astonishing. When a crack branches, it is often because the crack is moving fast enough that one path cannot handle the available energy smoothly, so it splits into multiple routes. That is why shattered glass can produce branching, lightning-like forms. Each branch is not just chaos, it is a new path for releasing stress. In dried mud, Cracking often forms networks because the shrinking surface is constrained by the ground beneath it. As the material dries and contracts, it cannot shrink freely everywhere, so tension builds and breaks into polygon-like patterns. In paint, clay, concrete, lava flows, old varnish, and even some foods, similar networks can appear because shrinking, cooling, or hardening creates stress that needs release. The pattern depends on thickness, drying rate, material strength, adhesion to the base, and the order in which cracks form. The first cracks change the stress for the next cracks, so the final pattern is a history of events, not a design placed all at once. Every line changes the future of the lines around it. That is why crack patterns can look organic, like rivers, roots, veins, or lightning, even though they arise from physical rules. Nature repeats certain shapes not because it is copying itself, but because different systems face similar problems. How to move through resistance, how to release tension, how to divide space, how to follow the path where energy can fall most easily. A crack is also strangely honest. It shows weakness without hiding it. It reveals that solid does not mean invulnerable. The hardest surfaces may be full of invisible conditions, and the smallest flaw can become important if the surrounding stress is right. This is why materials science is not only about making things strong, but about understanding how they fail. Failure teaches more than perfection because it exposes the route the forces were trying to take. A broken plate shows impact lines, a fractured rock shows pressure history, a cracked bone shows load and trauma. A damaged machine part can reveal whether it failed suddenly, slowly, from fatigue, corrosion, overheating, or poor design. To the trained eye, a fracture surface is not just broken material. It is a record. It has texture, direction, origin, speed, and sequence. Matter writes its autobiography in the way it comes apart. And maybe that is why cracks hold our attention. They are frightening because they interrupt wholeness, but fascinating because they make the invisible visible. They show where tension gathered, where resistance ended, where a hidden story broke through the surface. So the next time you notice a crack in glass, stone, paint, soil, or porcelain, do not see only damage. See a map of stress. See a path selected by structure, weakness, pressure, and release. See the tiny flaw that became a doorway. See the material trying until the last possible moment to remain one thing. And then ask yourself a deeper question. How many things around you and within you appear unbroken only because the forces inside have not yet found their sharpest point? How friction turns motion into heat. Every time you rub your hands together for warmth, you are watching motion die and return as heat, as if movement itself has been ground down into an invisible fire. It feels simple because your palms warm quickly, almost obediently, but the truth beneath that ordinary gesture is far more intimate. Friction is not just things rubbing. It is the hidden conversion of organized movement into disorganized molecular agitation. When your hands slide past each other, the motion begins in one clear direction. Your muscles push, your skin moves, and the action has a kind of order to it. But your skin is not perfectly smooth. No surfaces. Even polished metal, glass, plastic, wood, or skin contains tiny hills, valleys, ridges, and patches of attraction when viewed closely enough. When two surfaces touch, they do not meet everywhere at once. They meet at scattered microscopic contact points like mountain peaks touching mountain peaks. As one surface moves across the other, those tiny contact points catch, deform, break, reconnect, and scrape past each other. Some of the motion is spent bending small structures. Some is spent breaking weak attractions between atoms and molecules at the contact points. Some becomes tiny vibrations traveling through the material, and those vibrations are heat. Not heat as a glowing substance, not heat as something added from outside, but heat as the restless motion of particles inside matter. This is the secret. Friction takes large-scale motion you can see and direct, and spreads it into countless tiny motions you cannot see. A sliding book slows on a table because its movement is being redistributed into microscopic shaking within the book, the table, and the air around them. A car tire warms on the road because the rubber is constantly deforming, gripping, releasing, and flexing as it rolls. A metal drill bit grows hot because the cutting edge forces material aside, and the resistance turns mechanical work into thermal energy. A match lights because striking it across a rough surface creates enough localized heating to trigger chemical reactions in the match head. Nothing mystical is happening. Energy is changing form. Motion becomes internal disorder. Direction becomes vibration. A clear push becomes hidden warmth. And this explains why friction is both necessary and wasteful. Without it, you could not walk. Your shoes need friction against the ground, so your foot can push backward and your body can move forward. Without friction, every step would become a helpless slide. Your fingers need friction to hold a cup, turn a page, tie a knot, use a tool, or grip a steering wheel. Brakes need friction to slow a bicycle, a train, or a car, converting the vehicle's motion into heat in brake pads, discs, tires, and surrounding air. In that sense, every stop is a small heating event. The energy of motion does not vanish when the vehicle slows. It is scattered into warmth, sound, and tiny deformations. This is why brakes can overheat on long downhill roads, why racing cars need carefully designed brake cooling, and why the smell of overheated pads is the smell of motion being burned away too quickly. But friction also steals energy from machines. In engines, gears, bearings, and chains, unwanted friction turns useful motion into heat that must be managed. That is why lubricants matter. Oil does not simply make surfaces slippery in a casual sense. It places a thin layer between moving parts, reducing direct contact between microscopic rough spots. Instead of metal tearing against metal, layers of fluid shear and flow, making the motion smoother and reducing wear. But even lubricated systems produce heat because fluids resist motion too. There is almost always some cost when movement passes through matter. This cost is written into the world so deeply that you feel it in your own body. Slide down a rope too fast and your hands burn. Rub an eraser against paper and the eraser warms while tiny pieces tear away. Run your hand across carpet and you may feel warmth from the fibers resisting and flexing. Even when you cannot feel the heat clearly, it is usually there, spread thinly, diluted into the surrounding material. Friction often works quietly because the heat is shared with too much matter to become dramatic, but concentrated enough, and it becomes impossible to ignore. That is why re-entry spacecraft need heat shields. As they fall back through the atmosphere at enormous speed, they collide with and compress the air in front of them, creating extreme heating around the vehicle. It is not simply rubbing against air in the everyday sense. The physics includes compression, shocks, and intense energy transfer. But the deeper story is still the same. Fast, organized motion is being transformed into chaotic heat. The universe is very good at taking order and spreading it out. Friction is one of the everyday doors through which that happens. It is the reason a rolling ball eventually stops, not because motion has been destroyed, but because the ball's energy has been shared with the floor, the air, and the material inside the ball itself. It is the reason perpetual motion machines fail in the real world. No matter how clever the design looks, parts touch, fluids move, fields interact, supports flex, and energy leaks away into forms that are harder to recover. Friction is reality's quiet tax on motion. And yet it is not only a thief, it is also a maker of control, warmth, safety, and contact. You live in a world where friction prevents objects from slipping endlessly, where roads hold tires, where nails stay in wood, where knots stay tied, where mountains do not instantly slide apart, where your own body can meet the ground and move with intention. The same force that wastes energy also allows you to act. This is what makes friction so philosophically strange. It resists motion, but without resistance, motion would become meaningless. A world without friction would not feel free. It would feel unreachable. You could push, but not grip, step, but not walk, stop, but not rest, hold, but not keep. Friction gives consequences to contact. It turns touching into influence, and heat is the memory of that influence after the visible motion is gone. When your palms warm, they are remembering the work your muscles did. When brakes glow, they are remembering the speed of the machine. When a tool grows hot, it is remembering the resistance of the material it fought through. So the next time you rub your hands together on a cold morning, do not see only a habit of comfort. See a transformation happening in your skin. See ordered motion breaking into microscopic vibration. See roughness, attraction, deformation, and energy exchange beneath a gesture you barely think about. And then, let the deeper question rise quietly. How many forms of warmth in your life began as resistance? And how much of what slows you down is also teaching the world where your motion has been? Why rubber bounces? A rubber ball does not bounce because it refuses the ground. It bounces because for a fraction of a second, it lets the ground deform it and then takes its shape back. Watch one hit the floor in slow motion, and the familiar event becomes almost unsettling. The ball falls, touches the surface, flattens like a tiny collapsing planet, spreads outward under its own impact, pauses for an instant in a compressed state, and then springs upward as if the floor has thrown it back. But the floor is not doing most of the throwing. The real return comes from the rubber itself. Rubber is elastic, meaning it can change shape under force and then recover much of its original form. But its elasticity is not like a steel spring simply bending and straightening. Rubber has a stranger inner life. At the molecular level, it is made of long chain-like molecules, tangled and coiled in restless arrangements. When you stretch or squash rubber, those chains are forced into less relaxed positions. They become more aligned, more extended, less free to wiggle in the many random shapes they prefer. The material stores some of the impact energy in that distorted arrangement. Then, when the force is released, the chains rush back toward their more comfortable, curled, disordered state, and the ball pushes away from the surface. In a quiet way, rubber bounces because its molecules prefer freedom. They do not want to remain neatly stretched. They want to return to their tangled ease, and that return becomes motion. This is why a rubber band snaps back when stretched, why a tire deforms where it meets the road and recovers as it rolls, and why a ball can turn a downward fall into an upward leap. The bounce is stored motion coming back out, but no bounce is perfect. When the ball hits the ground, not all of its energy returns as upward movement. Some is lost inside the material as heat, sound, internal vibration, and tiny molecular rearrangements. Rubber is not a perfect spring. It is viscoelastic, which means it behaves partly like an elastic solid and partly like a slow, resisting material that dissipates energy. You can feel this difference if you compare a steel ball and a rubber ball. A steel ball may deform very little, but if the surface is hard enough, it can rebound sharply because it loses little energy to internal squishing. A soft rubber ball deforms much more visibly, but if the rubber absorbs too much energy internally, the bounce becomes dull. That is why not every rubber object bounces well. A soft eraser, a tire, a shoe sole, and a super ball are all rubbery, but they do not return energy in the same way. Their ingredients, structure, stiffness, and internal losses are different. A super ball bounces dramatically because it is made from a highly resilient rubber-like material designed to return a large fraction of impact energy. A kneaded eraser barely bounces because it absorbs and rearranges under force instead of snapping energy back efficiently. The mystery is not simply rubber equals bounce. The real question is how much of the impact energy the material can store temporarily, and how much it can return before that energy disappears into hidden motion inside itself. Temperature changes this story too. Warm rubber is often more flexible because its molecular chains can move and rearrange more easily. Cold rubber can become stiff, less responsive, and in some cases brittle, because the chains lose mobility. A ball that bounces well in a warm room may feel dead in freezing conditions. This is not because the ball has forgotten how to bounce, but because its inner chains cannot recover with the same speed and freedom. Materials have moods in a sense, but their moods are physical. Heat gives molecular motion room to breathe. Cold can lock it down. This is why winter tires use rubber compounds designed to remain flexible at lower temperatures, while ordinary rubber may harden and lose grip. The same hidden chain behavior that makes a toy bounce also helps determine whether a car can hold the road. Rubber became especially useful after the discovery of vulcanization, a process that uses sulfur or similar chemistry to create crosslinks between polymer chains. Raw natural rubber can be sticky, weak, and overly sensitive to temperature. Crosslinking turns loose chains into a more stable network. Imagine long strands tied together at many points, so when they are stretched, they cannot simply slide past one another permanently. They are pulled out of shape, but the network gives them a reason to return. This is why vulcanized rubber can be durable, elastic, and practical enough for tires, seals, hoses, balls, and countless everyday objects. The bounce of rubber, then, is not merely a property of softness. It is a property of an internal network that can be distorted without falling apart. The ground presses in, the chains shift, the network stores strain, and then the material recoils. But the surface matters too. Drop a rubber ball on concrete and it rebounds sharply. Drop it on thick carpet and the carpet deforms, absorbing energy before the ball can reclaim it. The bounce belongs to the whole collision, not just the ball. The ball, the floor, the speed, the temperature, the shape, and the material all participate. Even air inside a hollow rubber ball changes the event. A basketball or tennis ball bounces partly because the rubber shell deforms, and partly because the air inside is compressed, storing energy like a temporary cushion. That compressed air pushes back outward, helping the ball regain shape and lift away. If the ball loses air pressure, it feels flat because the internal push is weaker and more energy is lost in the collapsing shell. A solid rubber ball has no air chamber, so its rebound depends more directly on the elasticity of the material itself. This is why bouncing is not one single mechanism, but a family of recoveries. Sometimes it is polymer chains snapping back. Sometimes compressed air helps. Sometimes a stiff shell stores energy. Sometimes the floor steals it. What you call a bounce is really a brief negotiation over where the energy goes after impact. And perhaps that is what makes rubber so quietly fascinating. It survives impact by yielding. It does not stay rigid and proud. It flattens, bends, absorbs, rearranges, and then returns. Its strength is not in refusing deformation, but in not letting deformation become permanent. That is a very different kind of resilience from hardness. A glass marble may seem stronger until it cracks. A rubber ball seems weaker because it gives way, yet that giving way is exactly what allows it to come back. So the next time you drop a rubber ball and watch it rise again, do not see only a toy obeying a simple rule. See long molecules briefly forced out of comfort. See hidden networks storing impact without surrendering their identity. See energy pause inside a flattened shape and then reappear as upward motion. See a material that teaches, without words, that recovery is not the absence of change. Recovery is the ability to change and still return with enough of yourself intact to rise. How glue really sticks. A glued object looks as if two separate things have simply agreed to become one, but the real secret is stranger. Glue works by sneaking into the microscopic reality your eyes never see and making separation difficult from the inside. You press two pieces of paper together, repair a cracked mug, seal a wooden joint, or stick a label onto glass, and it feels like the glue is doing something almost primitive, like grabbing and holding. But glue does not hold because it has tiny hands. It holds because surfaces are never as smooth, clean, or simple as they appear. Under magnification, wood is a landscape of pores and fibers. Paper is a tangled forest of cellulose strands. Metal has scratches and oxide layers. Plastic has chemical personalities that can resist or accept bonding. And even glass has microscopic irregularities and traces of moisture. For glue to work, it must first spread into that hidden terrain. This first step is called wetting, and it matters more than people think. If a glue cannot spread over a surface, if it beads up or pulls away, then it cannot make close contact. And without close contact, there is almost nothing to hold. A good adhesive must flow enough to enter tiny gaps, touch as much surface as possible, and reach places where the material's own roughness becomes useful. Then, as the glue dries, cures, cools, or chemically reacts, it changes from a flowing substance into a resisting one. In that change, it traps itself inside the surface texture, grips by physical interlocking, and sometimes forms molecular attractions or chemical bonds with the material itself. So glue is not one single trick. It is a family of tricks. Some glues work because water or solvent evaporates, leaving behind a solid layer that clings to both surfaces. White school glue, for example, contains polymer particles suspended in water. When the water leaves, the polymers come closer together and form a flexible film that holds paper, cardboard, and porous materials well. Wood glue works beautifully on wood because it can soak slightly into the fibers, then harden into a joint that often becomes stronger than the wood around it. That is why a well-made wood joint may break in the wood before it breaks at the glue line. The glue did not merely sit between two boards like a weak layer of paste. It became part of the fibrous boundary where the two surfaces met. Other adhesives behave very differently. Superglue, or cyanoacrylate, cures rapidly when it meets tiny amounts of moisture on surfaces and in the air. It does not need to dry by losing water in the same way school glue does. Instead, its small molecules link together into long chains, hardening quickly into a rigid bond. This is why superglue can grab skin so fast. Your skin has moisture, texture, and chemistry that help the reaction begin. Epoxy is different again. It usually comes in two parts, a resin and a hardener, which react when mixed. The curing process creates a strong network that can bond metals, ceramics, glass, wood, and some plastics, depending on surface preparation and the exact formulation. Epoxy is less like a liquid that simply dries and more like a material being born between the surfaces. It starts as something spreadable and ends as a solid network. Hot glue has another strategy. It is melted by heat, flows into gaps while warm, then cools and solidifies. It is convenient and fast, but it may soften again with heat and often relies heavily on surface texture and shape rather than deep chemical bonding. Pressure-sensitive adhesives, like those on tape or sticky notes, are stranger still. They never fully harden into a brittle solid. They remain soft and slightly flowing at a tiny scale, able to press into surface roughness when you apply pressure, while still being elastic enough to resist being pulled away. That is why pressing tape down improves the bond. You are helping the adhesive make more intimate contact. And that also explains why dust, oil, and moisture can ruin adhesion. Glue needs access to the surface. If a thin layer of grease, dirt, oxidation, or loose powder sits between the adhesive and the object, the glue may bond to the contamination instead of the material. Then when you pull, the weak layer fails. This is why cleaning and sanding can make a glue joint much stronger. Sanding can increase useful surface area and create fresh texture, while cleaning removes the invisible barriers that stop the adhesive from approaching closely enough. But rougher is not always better. If a surface is too rough or poorly matched, air gaps may remain, and the glue may not reach everywhere. A strong bond is not just about roughness. It is about contact, compatibility, and the way the adhesive changes after application. This is why some plastics are notoriously hard to glue. Materials like polyethylene and polypropylene have low surface energy, meaning many glues do not spread on them easily or form strong attractions. The adhesive may peel away because it never truly became close to the plastic in the first place. Special surface treatments, primers, or specific adhesives are often needed. The lesson is simple but humbling. Stickiness is not universal. A glue that works perfectly on paper may fail on oily metal. A tape that holds cardboard may peel from silicone. A strong epoxy may still fail if the surface is dirty or if the joint is designed poorly. The shape of the joint matters because adhesives usually handle some kinds of stress better than others. Many glue joints resist sliding forces better than peeling forces. Peel a sticker from one corner, and you concentrate the force along a narrow moving edge, making removal easier. Try to slide the whole sticker sideways, and it may resist much more strongly because the force is spread across the bonded area. This is why engineers design bonded joints to avoid peel whenever possible. Glue is strong when the load is shared. It is vulnerable when the force is focused at an edge. Time also matters. Some glues feel set within minutes, but need hours or days to reach full strength, because curing reactions continue or water keeps leaving deeper parts of the joint. Temperature and humidity can speed or slow this process. Too much cold may keep an adhesive thick and unwilling to flow. Too much heat may weaken certain bonds. Too little moisture may slow some curing, while too much moisture may interfere with others. So when a label says clamp for 1 hour or full strength after 24 hours, it is not just a cautious instruction. It is a recognition that adhesion is a process, not a moment. The bond must develop. The material must settle into its final state. The hidden contact must become stable. And perhaps this is what makes glue so quietly fascinating. It teaches that connection is not the same as touching. Two surfaces can press against each other and still remain separate if nothing fills the microscopic distance between them. Glue works by entering that distance, adapting to it, hardening within it, and making the boundary harder to undo. It does not erase the fact that the objects were separate. It creates a new region between them, where both surfaces participate in the same resistance. So the next time you glue paper, repair wood, press tape onto a box, or watch a broken object become useful again, do not see only stickiness. See wetting, contact, curing, interlocking, molecular attraction, surface preparation, and stress moving through a hidden layer. See a liquid becoming a memory of pressure. See separation slowed down by chemistry. And then ask yourself the quieter question. How many things in the world only seem joined at the surface? And how many truly hold because something patient has entered the space between them and changed what separation means? Static electricity in clothes. Your clothes can turn into a silent electric machine simply by tumbling in the dark, rubbing against each other until invisible charges gather like weather under fabric. You pull a sweater from the dryer and it crackles. A sock clings to a shirt as if it has developed loyalty. A skirt sticks to your legs. A tiny spark jumps from your sleeve to a metal doorknob, sharp enough to make you flinch, yet too small to explain the strange feeling that your ordinary laundry has briefly become alive. But nothing supernatural is happening. Static electricity in clothes begins with one of the smallest imbalances in nature. Electrons being moved from one material to another. Atoms contain charged particles, and most objects around you usually feel electrically neutral because their positive and negative charges balance out. But when fabrics rub together, especially in a dry environment, some materials are more likely to give up electrons, while others are more likely to take them. This is called the triboelectric effect. It does not mean friction itself creates charge from nothing. It means contact and separation between different materials can transfer charge. When a polyester shirt rubs against a cotton towel, when nylon slides against wool, when socks tumble through a dryer with synthetic fabrics, electrons may shift. One piece of clothing ends up with extra negative charge. Another is left slightly positive. The imbalance may be tiny in total amount, but because fabric can be a poor conductor, those charges do not flow away easily. They remain trapped on the surface, waiting. That waiting is what you experience as static. The charge is stuck, not because it wants drama, but because many clothing materials are insulators. In a conductor like metal, excess charge can move freely through the material and spread out or escape into the ground. In dry fabric, charges often have nowhere easy to go. They sit in patches, building electric fields around the cloth, reaching outward into nearby objects. This is why your laundry clings. A charged shirt can attract a neutral sock because the electric field rearranges charges inside the sock slightly. The side closer to the shirt becomes more oppositely charged than the far side, so attraction wins. The sock does not need to be strongly charged from the beginning. It can be pulled simply because the charged fabric polarizes it, gently separating its internal charges just enough to create attraction. That is why static cling feels almost intentional. The fabrics seem to choose each other, but really the electric field is shaping the space between them. Dry air makes the problem worse because moisture helps charges leak away. Water molecules in humid air can settle on surfaces and make it easier for charge to move and dissipate. In winter, indoor air is often dry because heating systems lower relative humidity, and that dryness makes static electricity more noticeable. The same sweater that behaves quietly on a humid day may crackle violently on a cold, dry night. The material did not change its personality. The environment changed how long the charge could survive. This is why dryer sheets work. They often contain softening agents that coat fabric surfaces, reduce charge buildup, and make fibers less likely to cling. Fabric softeners can do something similar by making surfaces slightly more conductive or less prone to charge separation. Anti-static sprays add moisture or conductive compounds that help excess charge drain away. Even touching a grounded metal object before handling clingy clothes can reduce the imbalance, because you give charge a path to move. The little shock you feel when touching a doorknob is that path opening suddenly. Your body may have collected charge from walking across carpet or pulling off clothing. The metal doorknob is a conductor, often connected indirectly to a much larger electrical environment. When your charged hand comes close enough, the electric field becomes strong enough for air to briefly break down, and a spark jumps. Air normally resists electrical flow, but when the voltage difference is high enough across a tiny gap, the air becomes momentarily conductive. That spark is a miniature discharge, a tiny version of the same general principle behind lightning, though on an enormously smaller and safer scale. The snap is not caused by a large amount of energy compared with dangerous electrical sources. It is caused by charge moving very quickly through a small path. That speed makes it bright, sharp, and surprising. In clothes, static can also make fabric behave differently on your body. A charged garment may cling tightly because it is attracted to your skin or to another layer of clothing. Thin synthetic fabrics often show this strongly because they rub easily, hold charge well, and are light enough for small electric forces to move them. Heavier fabrics may still charge, but their weight and stiffness can hide the effect. This is why a light dress may cling dramatically while a thick coat does not seem to care. The strength of static effects depends not only on charge, but also on weight, texture, humidity, surface area, and how easily the material bends. Static is not just electricity. It is electricity meeting fabric structure. The weave, the fiber type, the dryness, and the motion all shape the final behavior. Inside a dryer, the conditions are almost perfect for static buildup. Clothes tumble, separate, collide, and rub over and over. Warm air removes moisture, making the fabrics drier. Synthetic materials exchange charge with natural fibers or with each other. As the load spins, pieces touch and separate thousands of times, each interaction offering another chance for charge transfer. By the end, the clothing may carry uneven islands of electric charge. Then you open the door, reach in, and the hidden field announces itself through crackles, clinging, and sparks. You are not seeing electricity as wires and circuits. You are seeing electricity as imbalance, as stored separation, as a charge that has not yet found its way home. And that is what makes static electricity in clothes such a strange teacher. It shows that power does not always flow continuously. Sometimes it accumulates quietly on surfaces. It waits in the folds of a shirt, in the space between a sock and a sweater, in the dry air around your hand. It is created by ordinary contact, preserved by isolation, and released when a path appears. The charge is invisible until it moves something, attracts something, or shocks you awake. In that sense, static electricity reveals a deeper pattern in the physical world. Many forces are not obvious while they build. They become visible only at the moment of imbalance. Your clothes cling because separated charges want balance. The spark jumps because nature has found a shortcut back toward equilibrium. The crackle is not chaos, it is return. So the next time you hear fabric snap in the dark, or feel a tiny sting from a sweater sleeve, do not dismiss it as a small annoyance. See electrons shifted by touch, trapped by insulation, strengthened by dry air, and released through sudden contact. See your laundry as a quiet storm system made of cloth, and then let the thought settle softly. Even the things closest to your skin can carry invisible tension. And sometimes all it takes is one small opening for the hidden charge to finally reveal itself. Why hair stands up. Your hair can rise before you even understand why, as if your body has already heard a message from the world that your conscious mind has not yet received. You feel it in a dark room after a sudden noise, during a cold wind across your neck, while listening to a song that moves through you too deeply, or when fear arrives so fast it seems to bypass thought. The tiny hairs on your arms lift, the skin tightens. A faint shiver travels across you. For a moment, your body becomes alert in a way that feels ancient, almost animal, because it is. Hair standing up is not just a random reaction or a poetic sign of emotion. It is a physical response built into your skin, controlled by nerves, muscles, temperature, fear, memory, and survival systems older than language. Each hair on your body grows from a follicle, and attached to many of those follicles is a very small muscle called the erector pili. When this muscle contracts, it pulls the hair more upright and creates the tiny bumps you call goosebumps. The name comes from the way plucked goose skin looks, but the mechanism belongs to mammals in general. In animals with thick fur, this response can be useful. When cold arrives, raised fur traps a thicker layer of air close to the body, helping insulation. When danger appears, raised fur can make the animal look larger, more threatening, harder to attack. A frightened cat arches its back and fluffs its fur. A dog's hackles rise. A porcupine's quills lift in warning. In humans, most body hair is too fine and sparse to provide much warmth or intimidation, but the old system remains. Your skin still carries the machinery of a fur-covered past. The muscle still pulls. The hair still rises. The body still performs a survival gesture whose original purpose has mostly faded, like an ancient ritual preserved in flesh. This is why goosebumps are often described as a vestigial response, meaning a leftover trait from earlier evolutionary conditions. But leftover does not mean meaningless. It means the body is layered with history. You are not only a modern mind moving through rooms, streets, screens, and conversations. You are also an animal body carrying old reflexes, old alarms, old ways of meeting cold and threat. When your hair stands up from fear, the signal usually begins in the autonomic nervous system, especially the sympathetic branch, the part that prepares the body for action. This system can change your heart rate, widen your pupils, release stress hormones, redirect blood flow, and tighten tiny muscles in the skin without asking your permission. It works below conscious control because survival often cannot wait for careful thought. If something rustles behind you at night, your body may react before you have identified the sound. That reaction is not stupidity. It is speed. The skin tightens, hairs rise, muscles prepare, attention sharpens. Your body is not saying, "I know there is danger." It is saying, "There might be danger, and we should be ready." This distinction matters because goosebumps often appear not only from real threats, but from imagined ones, remembered ones, symbolic ones. A horror movie can raise your hair even though you are safe in a chair. A memory can chill your arms even though the moment is gone. A piece of music can create goosebumps because your brain predicts, waits, and then receives a powerful emotional resolution, activating reward and arousal systems at the same time. In that case, the body is not defending against danger, it is responding to intensity. The nervous system uses some of the same physical switches for fear, awe, cold, beauty, and anticipation. This is why goosebumps can feel confusing. They appear during terror, but also during wonder. They rise at a funeral, during a national anthem, before a performance, in the middle of a prayer, or when someone says something that feels painfully true. The body does not always separate emotion into neat categories. It responds to importance. Something has crossed the threshold from ordinary to meaningful, and the skin becomes a surface where that meaning appears. There is also a direct thermal story. When your skin senses cold, receptors send signals that help trigger responses meant to preserve body temperature. Blood vessels near the skin can narrow to reduce heat loss. Shivering can begin to produce heat through rapid muscle activity, and the tiny muscles attached to hairs can contract, creating goosebumps. In a furrier animal, this would lift hair and trap insulating air. In you, it may not warm you much, but it still announces that your body noticed the cold before you decided what to do about it. Sometimes goosebumps appear after stepping out of a warm shower when evaporating water cools your skin. Sometimes they rise when a breeze moves across sweat. Sometimes they come when fever changes the body's temperature regulation, and the brain behaves as if you are cold, even while your internal temperature is rising. In all of these cases, hair standing up is not a mystery of the hair itself. Hair is mostly passive. The living command comes from the follicle, the muscle, the nerves, and the chemical signals of the body. The hair is only the flag. The body beneath it is the country moving. And this makes the reaction more intimate than it first appears. Your skin is not just a covering, it is a sensory field, a living border filled with nerves, blood vessels, immune cells, glands, follicles, and tiny muscles. It is constantly listening to temperature, pressure, vibration, pain, texture, and emotional state. When hair stands up, the skin is not merely showing something, it is participating in a whole body shift. The boundary between inner and outer becomes visible. Something outside touches you, or something inside rises, and the skin answers in form. Even the timing can teach you. Goosebumps can happen in waves, because the nervous system fires in patterns, and different regions of skin respond depending on sensitivity, hair density, temperature, and emotional strength. You may feel them begin at the neck, travel down the arms, or bloom across the scalp. That spreading feeling is part physiology, part perception, part attention. Once you notice the sensation, your mind may amplify it, turning a small skin response into a full body experience. The body and mind loop into one another. A chill becomes awareness. Awareness deepens the chill. A song lifts the hair. The lifted hair makes the moment feel even more powerful. This is how physical sensations become emotional proof. But it is important not to exaggerate the mystery. Hair standing up does not prove the presence of a ghost, a hidden truth, or a supernatural signal. It proves that your nervous system has reacted. That reaction may be triggered by real cold, real fear, real beauty, memory, expectation, surprise, or pattern recognition. The wonder does not need a false story to become fascinating. The truth is already strange enough. Tiny muscles in your skin contract because your brain and body judge a moment as biologically important. A microscopic movement becomes a visible sign of being alive. A reflex inherited from furred ancestors still appears when a modern human hears music through headphones in the dark. The past rises through the skin, so the next time the hairs on your arm lift without warning, do not dismiss it as a meaningless shiver. See an old survival system waking briefly inside you. See tiny muscles pulling at follicles. See your nervous system translating cold, fear, awe, or beauty into motion. See your skin remembering a time when raised hair could keep warmth close or make a frightened body look larger. And then sit with the quieter question beneath it all. How much of what you feel is not first spoken in words, but whispered through the body, rising through the skin before the mind has found a name for it? How touchscreens sense your finger. The glass on your phone is not waiting to be pressed. It is listening for the tiny electrical shadow of your body. You touch the screen, and an icon opens, a letter appears, a map moves, a video pauses, and the whole event feels so immediate that it seems almost like the device understood your intention before your finger fully arrived. But the screen is not reading your mind. It is reading a disturbance. Beneath the smooth glass is a carefully arranged grid of transparent conductive material, often made from a substance such as indium tin oxide, thin enough to let light pass through, but conductive enough to hold and sense electric charge. Modern phone screens are usually capacitive touchscreens, meaning they depend on capacitance, the ability of a system to store a small amount of electrical charge. The device creates a faint electrostatic field across this hidden grid. Your finger, because your body contains water, dissolved salts, and conductive tissues, interacts with that field when it comes close. You are not just a piece of flesh touching glass. To the screen, your finger is an electrical object connected to a much larger body. When it approaches the grid, it changes the local electrical conditions, slightly altering how charge is stored at that point. The change is tiny, but the electronics behind the screen are built to notice tiny changes very quickly. The touchscreen controller scans the grid again and again, looking for places where the expected electrical pattern has been disturbed. When it finds one, it calculates the position of your touch and sends that information to the phone's processor. The software then decides what that touch means. A tap, a swipe, a pinch, a long press, a drag, a command. The visible magic is really a chain. Your finger changes an electric field, sensors detect the change, the controller locates it, software interprets it, and the display responds. What feels like direct contact with a digital world is actually translation layered upon translation. Your finger never enters the app. It never touches the image. It only changes a field above a hidden grid, and the machine turns that change into meaning. This is why a normal plastic pen cap usually does nothing on a phone screen. Plastic is an insulator, and it does not affect the capacitive field the way your finger does. It may tap the glass physically, but the screen is not mainly looking for pressure. It is looking for an electrical presence. This is also why many ordinary gloves fail on touchscreens. The fabric separates your conductive finger from the glass and prevents the electric field from being disturbed strongly enough. Touchscreen gloves work because they include conductive threads or coatings that carry your finger's electrical influence through the glove to the screen. A capacitive stylus works for a similar reason. It must be designed to imitate the electrical effect of a finger, often with a conductive tip broad enough for the sensor grid to recognize. Older resistive touchscreens worked differently. They used pressure. They had flexible layers that physically touched when pressed together. So a fingernail, stylus, or any hard object could activate them. That is why older devices, some payment terminals, and certain industrial screens could respond to pressure even through gloves. But resistive screens usually lack the same clarity, smooth multi-touch ability, and light feel that capacitive screens brought to modern phones. Capacitive sensing made touch feel less like pushing a button and more like moving through light. Multi-touch is another hidden achievement. When you place two fingers on the screen to zoom a photo, the device must detect two separate disturbances at once, track their positions as they move, and interpret the changing distance between them. It must distinguish a pinch from a rotate, a scroll from a tap, a palm from a finger, an accidental brush from an intentional command. This is not just glass sensing touch. It is algorithms shaping touch into language. The screen provides raw electrical evidence, but software decides the gesture. It watches timing, movement, area, pressure estimates from contact size, and patterns learned from how humans use their hands. Palm rejection, for example, is especially important on tablets with styluses. If your palm rests on the glass while writing, the device must ignore one kind of contact while accepting another. It does this through sensor patterns, stylus signals, timing, and prediction. The screen is not intelligent in a human sense, but it is constantly sorting signals from noise, intention from accident. Even water can confuse it. A drop on the screen can conduct enough to disturb the field, creating false touches or making the screen behave unpredictably. Wet fingers may spread the electrical contact area in unusual ways. This is why screens can become strange in rain, or why a phone may misread touch when the glass is dirty, oily, cracked, or covered by a poor screen protector. The surface may look like a simple window, but its sensitivity depends on the relationship between glass, electric field, material, moisture, and signal processing. The screen also has to work while the display underneath is producing light, while the phone is handling radio signals, while the battery is conserving power, while the processor is predicting your next move. Every swipe is a coordination of hardware and software moving faster than your awareness can separate. The phone must sense where your finger is, update the image, animate the motion, and make the response feel attached to your body. If there is too much delay, the illusion weakens. The glass stops feeling alive and starts feeling like a barrier. This is why touchscreen latency matters. The less delay between touch and response, the more your brain accepts the screen as an extension of action. The device becomes convincing, not because it is truly immediate, but because the delay is small enough to disappear into perception. And maybe that is the deeper strangeness of a touchscreen. It turns electricity into intimacy. A machine made of glass, metal, minerals, circuits, and code becomes responsive to the soft conductivity of your skin. You do not press gears or flip switches. You disturb a field, and a world reorganizes itself beneath your fingertip. The screen has no nerves, yet it behaves as if it can feel. It has no skin, yet it detects presence. It has no understanding of desire, yet it opens the thing you reached for. That is the quiet illusion at the center of modern touch. The device does not know you, but it is built to respond so smoothly that response feels like recognition. So the next time you tap a screen in the dark and watch light answer your finger, do not see only a phone obeying a command. See a transparent grid waiting beneath glass. See your body altering an electric field. See sensors measuring a tiny disturbance. Software turning that disturbance into intention. And pixels rearranging themselves into consequence. And then ask yourself, softly, how much of modern life now depends on this invisible handshake? A human body reaching toward a silent field, and a machine mistaking that touch for meaning. Why microwaves heat water? A microwave oven does not heat your food with fire. It fills a metal box with invisible waves that persuade water molecules to turn their confusion into warmth. You place a cold bowl inside, close the door, press a button, and within moments, something that had no flame beneath it, no glowing coil touching it, no hot pan carrying heat into it, begins to warm from the inside of its own material. That feels almost suspicious, as if the machine is doing something unnatural. But the microwave is not making the food radioactive, and it is not injecting heat like a hidden gas. It is using electromagnetic waves, a form of energy related to radio waves and light, tuned in ordinary kitchen ovens to a frequency that interacts well with many foods, especially foods that contain water. Water molecules are electrically uneven. One side behaves slightly more positive, the other slightly more negative. So each molecule is a tiny polar object, not charged overall, but shaped in a way that responds to electric fields. Inside the microwave oven, the electric field of the microwaves changes direction extremely rapidly. Water molecules try to follow that changing field. They twist, rotate, hesitate, bump into neighboring molecules, lose track, and try again. They do not spin smoothly like perfect little motors. They are crowded, tugged, delayed, interrupted. And that delay is where heating begins. The energy from the wave is converted into the restless motion of molecules. In simple words, the microwaves make polar molecules attempt to reorient again and again, and their interactions with the crowded material around them turn that motion into heat. This kind of heating is often called dielectric heating, and it is not limited only to water, though water is one of the most important participants in everyday food. Some fats, sugars, salts, and other molecules can also influence how microwave energy is absorbed. But water is the reason soup, vegetables, rice, coffee, and leftovers often respond so strongly. The deeper truth is that a microwave oven is not heating the air around the food first, the way a conventional oven does. In a normal oven, hot air and hot surfaces warm the outside of the food, and heat slowly moves inward. In a microwave, the electromagnetic waves can penetrate into the outer region of the food and deposit energy directly within the material. But this does not mean microwaves cook perfectly from the inside out, which is one of the common myths. In many foods, microwave energy only penetrates a limited distance before being absorbed, often a few centimeters, depending on the food's composition, thickness, temperature, and moisture. The inner parts may still warm by ordinary conduction, as heat spreads from warmer regions to cooler ones. That is why a thick piece of food can come out hot on the edges and cold in the center. The microwave did not fail because it was weak. It failed because energy absorption and heat spreading are not the same thing. The waves may enter unevenly. The food may contain different amounts of water in different regions, and heat may not have had enough time to smooth itself through the whole object. This is why resting time matters after microwaving. When food sits for a minute, heat continues to move internally, reducing hot and cold spots. The pause is not wasted time, it is the food catching up with itself. The spinning plate also has a purpose. Inside the oven, Microwaves reflect from the metal walls and overlap, creating regions where the electric field is stronger and weaker. These patterns can make certain spots heat faster than others. The turntable moves the food through different parts of the field, so one place does not receive all the energy, while another stays neglected. Some ovens use stirrers or other designs to scatter the waves more evenly, but perfect uniformity is difficult because food is not uniform either. A bowl of soup, a piece of bread, a potato, and a frozen meal all absorb energy differently. A potato contains water trapped inside a dense structure, so steam pressure can build within it if it is not pierced, sometimes causing it to split. Bread can become tough because microwaves heat water inside it, and as that water moves or evaporates, the starch structure changes, making the texture rubbery or dry. Pizza can come out with a soft crust because microwaves do not brown and crisp surfaces the way hot air, hot metal, or infrared radiation can. Browning requires surface chemistry at higher dry temperatures, often after water has evaporated from the surface. A microwave is excellent at exciting polar molecules in moist regions, but it is not naturally good at making the dry, crisp, roasted outer layer your senses associate with fire. That is why microwave cooking can feel fast, but sometimes texturally incomplete. It warms efficiently, but it does not always create the same surface story as a pan or oven. Frozen food adds another strange layer. Ice does not absorb microwave energy in exactly the same way liquid water does, because the molecules in ice are locked into a more rigid structure and cannot reorient as freely. As parts of frozen food begin to melt, those liquid regions can start absorbing microwaves more effectively, heating faster than still frozen parts. This can create uneven thawing, with some pockets hot while others remain icy. It is not randomness. It is a feedback loop between state, structure, and absorption. The parts that melt become better at absorbing, so they can race ahead, stirring, rotating, covering, using lower power, and allowing pauses can help reduce this imbalance because they give heat time to spread, rather than letting the most responsive zones dominate. The metal walls of the microwave oven are also essential. They reflect the waves and keep much of the energy inside the cooking chamber, while the mesh in the door has holes small enough to block the microwaves, but large enough for visible light to pass through, letting you see inside. The oven is a cage for waves, not a magical box. Metal objects inside can be dangerous or unpredictable, not because all metal is instantly forbidden in every possible form, but because sharp edges, thin foil, or certain shapes can concentrate electric fields and cause sparks or arcing. Smooth, properly designed metal parts can exist safely in some microwave accessories, but random metal utensils are risky because they can reflect waves, create electrical hotspots, damage the oven, or ignite nearby material. Microwave-safe containers matter for a different reason. The container should not melt, release harmful substances under heating conditions, or absorb too much microwave energy itself. Many ceramics and glasses allow microwaves to pass through mostly into the food, while some plastics may warp or degrade if not designed for the job. The machine is heating the food, but the container still lives in the same environment and must survive the heat the food produces. And perhaps the most important myth to dissolve is the fear that microwaved food becomes radiation-filled. Microwaves are non-ionizing radiation, meaning they do not carry enough energy per photon to break chemical bonds the way X-rays or gamma rays can. They can heat tissue if exposure is strong enough, which is why the oven is shielded, but they do not remain stored in the food after the oven stops. When the magnetron stops producing microwaves, the waves quickly disappear, and what remains is simply warmed food. The energy has become molecular motion, the everyday thing you know as heat. In that sense, a microwave oven is less like a poison machine and more like a translator. It translates an oscillating electric field into molecular agitation. It turns invisible waves into lunch. It makes the water inside food participate in its own warming. And there is something quietly profound in that. Heat does not always need to arrive from the outside like a command. Sometimes the right kind of energy enters a material and asks its own hidden structure to respond. The food warms because its molecules are not neutral to the invitation. They have shape, polarity, freedom, delay, and resistance. They answer the field imperfectly, and that imperfection becomes warmth. So the next time you hear the low hum of a microwave and watch a bowl rotate behind the glass, do not see only convenience. See invisible waves reflecting through a chamber. See water molecules trying to follow a field that changes too fast to obey cleanly. See motion becoming disorder, disorder becoming heat, and heat spreading through the food after the machine falls silent. And then let the ordinary scene become a little stranger. Your meal is not being touched by flame, yet it is being warmed by a hidden conversation between fields and molecules, between the unseen rhythm of electricity and the quiet water inside everything that once lived. How refrigerators move heat backward. A refrigerator does something that feels almost like cheating nature. It takes heat from a colder place and throws it into a warmer room, but only because electricity pays the price. When you open the door and feel that cool air spill against your skin, it is tempting to imagine that the machine is creating cold, as if cold were a substance being poured into the shelves. But cold is not something a refrigerator makes. Cold is what remains when heat has been removed. The true work of the refrigerator is not to produce winter inside a box, but to move thermal energy out of that box again and again, quietly fighting the natural tendency of heat to flow from warmer things into cooler things. Left alone, the food inside would slowly warm until it matched the kitchen, the walls, the air, the milk, the fruit, the leftovers. Everything would drift toward the same temperature as the room, because nature prefers balance. The refrigerator prevents that balance by acting like a heat pump. It uses a special fluid called a refrigerant, a compressor, coils, and pressure changes to carry heat from the inside to the outside. The process begins in the hidden cold coils inside or behind the freezer and refrigerator compartment, where the refrigerant is at low pressure and very cold. Because it is colder than the air and food around it, heat naturally flows from the refrigerator interior into the refrigerant. As the refrigerant absorbs that heat, it evaporates into a gas. This is the first trick. The refrigerant is chosen because it can change between liquid and gas at useful temperatures, absorbing a large amount of heat as it evaporates. The air inside the fridge loses energy to the refrigerant, and that is why the compartment stays cold. A fan may help move air across the coils, spreading the cooling effect, but the deep action is happening in that circulating fluid. The refrigerant is not destroying heat. It is picking it up like a courier. Then the compressor enters the story. It squeezes the refrigerant gas, raising its pressure and temperature. This part is essential because the refrigerant that just absorbed heat from the cold interior must now be hot enough to release that heat into the warmer kitchen. Without the compressor, heat would not willingly leave a cold place and enter a warmer one. The compressor gives the refrigerant a push upward, energetically speaking, making it hotter than the room air. Then the hot, high-pressure refrigerant flows through the condenser coils, often on the back or underneath the refrigerator. There, heat flows from the refrigerant into the kitchen air. This is why the back of a refrigerator can feel warm. The machine is not leaking energy by accident. That warmth is the heat removed from your food, plus the extra energy added by the compressor's work. Your refrigerator cools the inside by warming the outside. It creates a small region of low temperature only by dumping heat somewhere else. After releasing heat, the refrigerant condenses back into a liquid. Then it passes through a narrow expansion device, where its pressure drops suddenly. As the pressure falls, the refrigerant becomes cold again and returns to the evaporator coils, ready to absorb more heat from inside the box. The cycle repeats. Absorb heat inside, compress, release heat outside, expand, become cold, absorb again. It is a loop of controlled transformation. A machine built around the fact that pressure changes can change how easily a fluid evaporates or condenses. The refrigerator is not violating physics. It is obeying physics very carefully. It moves heat backward only because energy is supplied from the electrical outlet. That electricity powers the compressor, and the compressor makes the impossible-looking direction possible. This is why leaving a refrigerator door open does not cool the room. It actually warms the room overall. The fridge may blow cool air from the open compartment for a moment, but the condenser coils release all the heat removed from that air, plus the heat created by the compressor's energy use. With the door open, the machine becomes a room heater pretending to be a cooler. The cold interior can only exist when it is enclosed, insulated, and protected from constant warm air entering. Insulation slows heat from leaking inward through the walls. The rubber door seal keeps warm air from sneaking around the edges. The thermostat watches the temperature and tells the compressor when to turn on and off. Every time you open the door, warm, moist air enters. The refrigerator must remove the extra heat from that air, and if enough moisture enters the freezer, that moisture can freeze onto cold surfaces as frost. Frost may look harmless, but it can act like insulation on the coils, making heat transfer less efficient and forcing the machine to work harder. That is why many modern refrigerators use automatic defrost systems. They periodically warm parts of the cooling system just enough to melt accumulated ice, then return to cooling. Even the placement of food matters. If air cannot circulate, some areas stay colder or warmer than others. If hot food is placed inside, the fridge must remove that added heat. If the coils outside are covered in dust, they cannot release heat efficiently into the room, and the compressor may run longer. A refrigerator, then, is not a magic cabinet. It is a controlled battlefield against heat leakage, moisture, pressure, and time. And the strangest part is that the machine depends on the same basic truth that makes your breath fog in winter, or sweat cool your skin. Changing state can carry a lot of energy. The refrigerant is useful because it can absorb heat while evaporating and release heat while condensing, over and over, without being used up under normal operation. It is a working fluid moving through a sealed loop, but the heat it carries is very real. The apple cools because its heat migrates into the air and then into the refrigerant. The milk stays safe longer because lower temperature slows the growth of many microbes and slows chemical reactions that spoil food. The freezer preserves not because it stops time completely, but because it slows the molecular and biological processes that would otherwise keep changing the food. A refrigerator is, in that sense, a machine for slowing decay. It does not defeat time. It negotiates with it by removing energy from the place where change would happen faster. And this gives the ordinary kitchen appliance an unexpected depth. Inside that humming box is a small rebellion against equilibrium. The universe tends to spread energy out, to let warmth wander, to blur differences until everything settles. But the refrigerator maintains a difference. It keeps one space colder than its surroundings by constantly doing work. It reminds you that order often has a cost. Freshness has a cost. Preservation has a cost. A cool interior requires heat to be expelled elsewhere, and stability requires energy moving through a system. So the next time you hear the low hum of a refrigerator at night, do not hear only an appliance running in the background. Hear a compressor lifting heat out of a cold chamber. See refrigerant carrying invisible warmth through hidden coils. See pressure changing the behavior of matter. See the kitchen being warmed slightly so the food can remain cold. And then let the quiet questions settle. How many peaceful spaces in life only stay peaceful because something unseen is working constantly, moving the heat away before you ever notice it was there? Why fans cool skin? A fan does not create cold. It steals the warm, wet silence clinging to your skin and replaces it with moving air. That is why the breeze from a fan can feel like relief, even when the air in the room has not actually become cooler. If you place a thermometer in front of a fan, the number usually does not drop in any meaningful way, because the fan is not removing heat from the room the way a refrigerator does. It is mostly pushing air around, and yet your body insists that something has changed. Your skin feels lighter, sweat dries faster. The heavy layer of heat around you seems to break apart. The reason is that your body is not a thermometer sitting in a room. Your body is a warm, living surface, constantly producing heat, constantly trying to release that heat into the environment. Even when you are resting, your cells are using energy, your organs are working, your muscles are quietly maintaining tone, and all of that activity produces warmth. To stay alive, you must get rid of excess heat. Your skin is one of the main places where that exchange happens. When the air is still, a thin layer of warm air builds up close to your body. It is like an invisible blanket, not thick enough to see but real enough to matter. Your skin warms the air touching it, and if that air stays near you, heat leaves your body more slowly. A fan disrupts that boundary. It pushes the warmed air away and brings in air that has not yet been heated by your skin. This allows heat to move from your body into the surrounding air more effectively. That process is called convection, but you can think of it simply as moving air carrying away the warmth your skin is trying to release. The fan does not need to make the room colder to make you feel cooler. It only needs to remove the air that your body has already warmed. But the deeper cooling comes from sweat. Sweat is not just water appearing on your skin as a sign of discomfort. It is your body's evaporative cooling system. When sweat evaporates, it changes from liquid on your skin into water vapor in the air. And that change requires energy. Much of that energy comes from heat on your skin, so evaporation carries heat away from you. This is why sweating can cool you even when the air itself is warm. But sweat only helps if it can evaporate. If the air near your skin is already humid and still, evaporation slows down. Sweat may drip without cooling you much, because liquid sweat running off your body has not taken as much heat away as sweat that evaporates from your skin. A fan helps by sweeping away the humid air that gathers around you and replacing it with drier or at least less saturated air from elsewhere in the room. This gives more sweat molecules the chance to escape into the air. That is the real reason a fan can feel almost magical on damp skin. It is not cooling the sweat directly like ice. It is helping the sweat leave, and in leaving, the sweat takes heat with it. This is also why a fan feels much less useful when you are completely dry and the air is extremely hot, or when humidity is so high that evaporation struggles. The fan can still increase heat loss if the air is cooler than your skin, but if the air is hotter than your body, especially during dangerous heat conditions, blowing that air across your skin can sometimes add heat instead of removing it. In those situations, a fan may feel like movement without real safety, especially for people who cannot sweat well, are dehydrated, elderly, ill, or exposed for long periods. The body's cooling system depends on several conditions working together: air temperature, humidity, sweat production, hydration, air movement, clothing, and how much heat your body is producing. A fan is powerful because it improves one part of the system, but it is not a shield against every kind of heat. This is why the same fan can feel wonderful on a warm evening, weak in a humid room, and almost like an oven wind in extreme heat. The physics has not changed. The balance has. Clothing changes the experience too. Loose fabrics can let moving air reach the skin and carry moisture away, while thick or tight clothing can trap warm air and humidity close to the body. This is why a breeze through a loose shirt can feel cooler than air blowing against a heavy jacket. The fan is not simply touching you. It is negotiating with the microclimate around your body, the tiny private atmosphere between your skin and the world. Hair, fabric, sweat, posture, and even the shape of your body influence how air moves across you. When you sit still in a warm room, that private atmosphere can grow stagnant. When the fan begins, it breaks the stagnation. It turns your skin from a sealed border into an exchange surface again. This also explains why moving air feels cooler while cycling, running, or riding in a car with the window open. Your motion through the air creates a similar effect. The air close to you is constantly replaced, sweat evaporates more easily, and heat is carried away faster. But once you stop moving, the warm layer returns. The body does not experience the environment as a fixed number. It experiences a relationship between heat production and heat removal. A fan changes that relationship. It makes the body's escape route wider. And there is something quietly humbling about that, because it means comfort is often not created by changing the whole world, but by changing the thin layer where you meet it. A room can remain the same temperature, and yet your skin can feel transformed because the air touching you no longer sits there like a closed door. The fan opens that door again and again with every turn of its blades. The blades themselves are shaped to push air, creating a pressure difference as they spin. They do not slice the air into coldness. They accelerate it, guide it, and send it outward as a stream. Behind the fan, air is pulled in to replace what was pushed forward, creating circulation through the room. This circulation can help even out pockets of warmer and cooler air, but the main sensation on your skin comes from the moving stream interacting with your body's heat and sweat. That is why pointing a fan at an empty room may not change much, but pointing it at your body can feel immediate. The machine is not cooling space as much as it is helping your body cool itself. In that sense, the fan is less like an artificial winter and more like a partner to your biology. It does not do the entire job. It assists the ancient system already built into your skin. Your sweat glands release moisture. Your blood vessels near the surface can widen to bring warm blood closer to the skin. Your skin offers heat to the air. The fan carries that heat and moisture away. It is a collaboration between machine and metabolism, between spinning blades and living tissue. And maybe that is why the sound of a fan at night can feel so comforting. It is not only noise, it is the sound of exchange being kept alive, the sound of air refusing to become still around you. So the next time a fan cools your face on a hot day, do not imagine it creating cold from nothing. See the warm layer near your skin being swept away. See sweat turning into vapor and taking heat with it. See humidity being disturbed, air replaced, your body's hidden heat given a path outward. And then let the ordinary breeze become a quiet lesson. Sometimes relief does not come from changing the temperature of the entire world, but from moving what has been trapped too close to you. Why mirrors reverse depth? A mirror is not secretly swapping your left and right. It is doing something stranger and more intimate. It is reversing the direction of depth, turning the world in front of the glass into a ghost space behind it. You stand before it, raise your hand, tilt your head, lean closer, and the person inside the mirror obeys with perfect timing. Yet something feels wrong in a way you learn to ignore. The face is yours, but not quite the one others see. The room appears to continue beyond the wall, but you know there is no room there. The glass is flat, silent and thin, yet it opens what looks like a second world with distance, position, and presence. That illusion begins with reflection. A good mirror has a very smooth reflective layer, often metal behind glass, where incoming light does not scatter randomly in all directions the way it does from paper, cloth, skin, or painted walls. Instead, light bounces off in an organized way. Rays arriving from one point on your face reflect toward your eyes in a pattern your brain interprets as if they came from a point behind the mirror. Your brain is not foolish for doing this. In everyday life, light usually travels in straight paths from objects to your eyes, so your visual system traces the reflected rays backward and constructs a virtual image behind the glass. That image is not physically sitting there. If you reached behind the mirror, you would find wall, wood, plaster, dust, wires, maybe nothing interesting at all. But optically, the image behaves as if it is there, the same distance behind the mirror as you are in front of it. Take one step closer, and your reflected self seems to step one step closer from the other side. Move away and the mirror world deepens. This is the first quiet trick. A mirror creates apparent depth without creating space. It gives your eyes geometry and your brain supplies a world. But the deeper misunderstanding is the famous idea that mirrors reverse left and right. They do not choose left and right. They reverse front and back, the axis pointing into and out of the mirror. Imagine pressing your palm toward the glass. In the real world, your palm faces forward toward the mirror. In the reflection, the palm of the mirror hand appears to face back toward you, as if the hand has been turned through the surface. The mirror has inverted the direction perpendicular to its plane. It has not taken east and west and traded them. It has taken toward the mirror and made it appear as away from the mirror. The reason this feels like left-right reversal is psychological, not because the mirror has a special preference for horizontal direction. When you look at another person facing you, you imagine them as someone who has turned around to face you. A real person opposite you has their right hand on your left side because they rotated in space. But your mirror image has not rotated like a person. It is a front-back inversion. It faces you without performing the turn a real body would need. That is why it feels reversed. The mirror image is like a version of you pulled through the glass, not a version of you who walked around and faced you. This is also why writing looks backward in a mirror. If you hold a word on a page facing the mirror reverses the direction pointing into the page and back out toward you. The front of the paper and the back of the paper are optically exchanged in the reflection. To read the reflected text comfortably, you would need to imagine the writing flip through the surface, not simply slid sideways. A transparent sheet can reveal the trick. If words are written on clear plastic and you turn it around to face someone, the writing appears reversed because you rotated the physical object, not because the mirror has some unique obsession with left and right. The mirror preserves up and down, preserves sideways directions across its surface, but reverses the depth direction, and your mind translates that into the eerie feeling of a swapped self. This is why your reflection feels both exact and alien. It matches your movements, but it has opposite-handedness. If you part your hair on one side, the reflection seems parted on the other. If you have an asymmetrical smile, scar, eyebrow, or gesture, the mirror returns it in a way that feels normal to you, only because you have seen that version so often. A photograph can feel strange for the same reason. Other people are used to seeing your non-mirrored face, but you are used to seeing the mirror version. The face you call familiar may be the one that reverses your depth. This is not vanity. It is perception adapting to the image it receives most often. The mirror becomes a teacher of how personal reality can be built from repetition. Even the apparent size and distance in a mirror obey a quiet structure. If you stand 2 meters from a flat mirror, your virtual image appears 2 meters behind it. So your eyes treat the reflected person as if they are 4 meters away from you in total light path. That is why focusing on yourself in a mirror is not the same as focusing on the glass surface. Your eyes adjust as if looking into depth. The mirror has no tunnel, but your visual system behaves as if there is one. This is why mirrors make rooms feel larger. They do not expand the room physically. They provide light patterns consistent with space continuing beyond the wall. Interior designers use this because your brain is deeply willing to believe in optical continuation. If light arrives with the right order, space is assumed. And yet the mirror remains brutally honest in another way. It does not store the object. It does not understand the face. It does not know the difference between a person, a lamp, a doorway, or an empty chair. It returns angles. It organizes light. Meaning is added by you. That is why a mirror can become emotional without being alive. It shows a body aging, a room changing, eyes tired, posture guarded, a smile practiced, a stranger who is also you. The physics is clean, but the experience is not. You are watching reflected light, but you are also confronting identity in reversed depth. The mirror gives you evidence and illusion at the same time. It shows your surface with remarkable precision, while hiding the fact that this surface is not the view others receive. It seems to reveal you, but it reveals you through a geometric transformation. There is a tenderness in that, and a warning. Seeing is not the same as receiving truth untouched. Even the simplest reflection is already an interpretation, first by light, then by optics, then by the brain, then by memory. A mirror does not lie, but it does not tell the whole truth either. It gives a lawful inversion and lets your mind call it reality. So the next time you stand before a mirror and feel that familiar self looking back, pause for a moment before accepting the image too quickly. See the smooth surface sending light back in organized paths. See your brain placing a virtual room behind the glass. See depth reversed, not left and right magically swapped. See a version of you that faces you without ever turning around. And then let the quiet question settle. How many things in your life feel familiar, not because they are complete, but because you have learned to live inside their reflection? Why rainbows curve? A rainbow does not curve because it is painted across the sky. It curves because every raindrop is sending color back to you from one precise angle, and your eyes are standing at the tip of an invisible cone. You look up after rain, when sunlight breaks through the clouds, and the arc appears so gently that it feels almost personal, like the sky has opened a colored doorway just for the moment you happen to be there. But the rainbow is not a physical object hanging in the distance. You cannot walk toward it and arrive beneath it. You cannot touch its edge. Two people standing in different places do not see the exact same rainbow because each person receives light from a different collection of raindrops. The rainbow belongs to the geometry between the sun, the droplets, and your eyes. For it to appear, the sun must usually be behind you, and rain or mist must be in front of you. Sunlight, which looks white to your eyes, enters countless tiny water droplets suspended in the air. As it enters a droplet, the light slows and bends because it is moving from air into water. This bending is called refraction. But sunlight is not a single simple thing. It is made of many colors mixed together, and those colors bend by slightly different amounts as they pass through water. Violet bends more than red. The colors begin to separate. Then, inside the droplet, some of the light reflects off the back inner surface, like a tiny mirror made of water, and travels back toward the front. As it leaves the droplet, it bends again, separating the colors even more. After this journey, each color exits the drop most strongly at a particular angle. Red light that reaches your eye from a primary rainbow usually comes from droplets positioned along one angle from the direction opposite the sun, while violet comes from a slightly smaller angle inside it. That difference in angle is why red appears on the outer edge and violet on the inner edge of the main rainbow. The curve appears because all the droplets sending the right color to your eye form a circle around a special point called the antisolar point, the point directly opposite the sun from your perspective. You rarely see the full circle because the ground blocks the lower part. From an airplane, mountain, or high place with mist below, you can sometimes see more of the circle, and under the right conditions, a rainbow can appear as a complete ring. This means a rainbow is not truly an arch. It is a circle mostly hidden by the horizon. The sky has not chosen a bridge shape. Your viewpoint has cut a circle in half, and that changes the feeling of the phenomenon. What seemed like a distant colored band is actually a slice through a three-dimensional cone of light, with your eye at the point of the cone and the rain-filled air forming the glowing boundary. Every droplet in that boundary is not glowing with the whole rainbow. Each one sends only certain colors to your eye depending on its position. Droplets above the arc, below it, or beside it may also be bending sunlight, but their light does not reach your eye at the correct angle to become part of the rainbow you see. The rainbow is selective. It is not where the rain is. It is where light, water, and your position agree. This is why the rainbow moves when you move. The raindrops are not carrying the same fixed image for everyone. Your rainbow is built from the droplets that fit your line of sight. Another person a few meters away receives a slightly different set. You share the event, but not the exact object. There is something deeply strange in that. One of the most public sights in nature is privately assembled in each observer's eyes. The colors are real light. The droplets are real. The physics is real, but the rainbow as a visible form is relational. It exists as an appearance created by alignment. The brightness of a rainbow depends on many conditions: how strong the sunlight is, how many droplets are in the air, how large and uniform those droplets are, how dark the background sky is, and how much light is scattered away by clouds or haze. Large raindrops can make brighter, more vivid colors, while very tiny droplets, like fog or mist, can create pale white or faintly colored fog bows because the color separation becomes softened by wave effects and scattering. Sometimes you see a second rainbow outside the first. This secondary rainbow forms when light reflects twice inside the droplets before leaving. Because of that extra internal reflection, the colors appear reversed. Red is on the inside and violet on the outside. It is also dimmer because each reflection inside the droplet loses some light. Between the primary and secondary rainbows, the sky can appear darker. This darker region is sometimes called Alexander's band, and it happens because less light is sent toward your eye from that range of angles. Even the spaces around the rainbow are shaped by optical rules, not just the colored arc itself. Under very good conditions, you may notice faint extra bands just inside the main rainbow, delicate greenish, pinkish, or purple fringes called supernumerary bows. These come from the wave nature of light. where light traveling along slightly different paths through droplets can strengthen or weaken itself when the paths meet. You do not need heavy mathematics to understand the wonder. The rainbow is not only a prism effect, it is also a wave effect when the droplets are small and similar enough. Light is bending, reflecting, separating, overlapping, and arriving in patterns your eyes translate into color. And the colors themselves are not sharp bands in the world. They blend continuously. Your brain divides them into familiar names: red, orange, yellow, green, blue, violet. The rainbow does not know these categories. It is a smooth spread of wavelengths, and your perception turns that spread into a ladder of color. That means the rainbow is both outside you and inside you. Outside, sunlight interacts with water droplets according to physical laws. Inside, your eyes and brain organize that light into the experience of colored beauty. The arc is not imaginary, but neither is it independent of the observer. It is one of the clearest examples of nature showing that seeing is a partnership. The world provides structure and your position completes it. The rainbow's curve is therefore a lesson in perspective. It tells you that some forms are not objects, but relationships. They appear only from certain places, under certain conditions, when light returns to the watcher in just the right way. Move the sun, move the rain, move yourself, and the rainbow changes or disappears. Nothing has to be broken for the beauty to vanish. The alignment simply ends. That is why rainbows feel fragile, even though the physics behind them is dependable. They are made from countless ordinary droplets, but the moment feels rare because the arrangement is rare. Sunlight must emerge while rain still falls. The sky must clear in one direction and remain wet in another. You must stand where the geometry can close around your sight. For a short time, the world becomes a lens, and you become part of the instrument. So the next time a rainbow appears, do not see only a colored arc after rain. See sunlight entering millions of droplets, bending into separate colors, reflecting within tiny spheres of water, bending again, and returning to your eye from the surface of an invisible cone. See the missing circle hidden below the horizon. See a personal rainbow built from your exact place in the world, and then let the quiet thought deepen. Sometimes, beauty is not a thing waiting out there to be found, but a meeting point between the world and the one who happens to be looking from the right angle. Why sunglasses reduce glare? Glare is not just brightness. It is light that arrives too organized, too concentrated, and too aggressively aimed at your eyes. You know the feeling when sunlight flashes off a wet road, a car windshield, ocean water, snow, polished metal, or a pale concrete sidewalk. And for a moment, the world does not simply look bright. It becomes hostile. Details vanish, shapes flatten. Your eyes narrow before you decide to squint. Your face turns away, as if your body is trying to protect the brain from too much information arriving at once. Sunglasses help because they do not merely make the world darker. Good sunglasses manage light before it reaches the delicate tissue inside your eyes. Ordinary tinted lenses reduce the total amount of visible light, lowering intensity, so your pupils do not have to fight as hard. That alone can bring relief on a bright day. But glare is more specific than general brightness. Much glare comes from light reflecting off flat surfaces, especially surfaces like water, roads, glass, snow, or sand. When sunlight scatters from rough objects, it tends to bounce in many directions, becoming mixed and less orderly. But when it reflects from a smoother surface at certain angles, much of it becomes polarized, meaning the light waves are vibrating more strongly in a particular orientation. You do not see this orientation directly, but your eyes feel the consequence. A harsh sheet of brightness that seems to wash across the scene. Polarized sunglasses are built to block much of that organized reflected light. Inside the lens is a special filter that allows light vibrating in one orientation to pass, while absorbing much of the light vibrating in the troublesome reflected orientation, often the glare coming from horizontal surfaces. That is why polarized sunglasses can make water look clearer, because they cut the bright reflected layer on the surface and let you see more of what lies beneath. It is why fishermen use them to see into shallow water, why drivers may find wet roads less blinding, and why snow glare can become less painful. The lens is not simply dimming everything equally. It is selecting. It is saying, in a quiet optical language, this kind of light may pass, and this kind must stop. But polarization is only one part of the story. Sunglasses also protect comfort by reducing the strain caused by excessive brightness. In strong sunlight, your pupil contracts to limit the amount of light entering the eye. You may squint using your eyelids as a crude narrowing device. Squinting reduces incoming light and can sharpen focus slightly, but it creates muscle tension and fatigue. Sunglasses take over part of that labor. By lowering brightness, they let your eyes remain more relaxed, while still receiving enough information to navigate the world. This is especially important in environments where light comes not only from above, but from below and around you. Snow is powerful because it reflects a large amount of sunlight in many directions. Sand and pale stone can do something similar. Water adds moving flashes that change moment by moment. In those conditions, your visual system is not only dealing with brightness, it is dealing with contrast overload, reflections, and rapid changes that can tire attention. A good pair of sunglasses makes the scene less visually violent. It gives the brain a cleaner signal to interpret. The color of the lens can also shape what you perceive. Gray lenses tend to reduce brightness, while keeping colors relatively natural. Brown or amber lenses can increase contrast in some conditions, making edges and depth feel clearer, though they alter color balance. Yellow lenses may help in low light or hazy conditions for some tasks, but they are not ideal for strong sunlight because they may not reduce brightness enough. Darker is not automatically safer or better. In fact, very dark lenses without proper ultraviolet protection can be risky because they cause your pupils to open wider while still allowing harmful ultraviolet radiation through. This is one of the most important truths about sunglasses. UV protection is not the same as darkness. A nearly clear lens can block ultraviolet light if it is made with the right material or coating, while a dark, cheap lens without UV protection may only trick your eyes into opening the gate wider. Ultraviolet light is invisible, but long-term exposure can contribute to eye problems, including damage to the surface of the eye and increased risk of cataracts over time. So the real value of sunglasses is not only comfort, it is protection from light you cannot see, not just light you can. This makes sunglasses a strange kind of shield. They protect you from both the visible assault of glare and the invisible burden of radiation. Some lenses add anti-reflective coatings on the back surface because light can also enter from behind or the sides and bounce off the inner face of the lens into your eyes. This is why high-quality sunglasses are not only about the front tint. The whole optical system matters. Lens material, UV filtering, polarization, coatings, curvature, fit, and how much stray light enters around the frame. Wraparound sunglasses can help in harsh environments because they block light from the sides. Mountaineers and people in snowfields may need serious protection because intense sunlight and strong reflection can lead to painful temporary injury, sometimes called snow blindness, where ultraviolet exposure damages the outer surface of the eye. Again, the danger is not always what feels brightest. Some of the most damaging light is invisible, and yet sunglasses are not perfect for every situation. Polarized lenses can make some digital screens harder to see because many screens emit polarized light of their own. Tilt your head while wearing polarized sunglasses and a phone, car display, or fuel pump screen may darken or show strange patterns. Polarization can also hide certain reflective cues, such as icy patches or wet spots, depending on conditions. So drivers and pilots must understand what their lenses are doing. The same filter that removes glare can sometimes remove information. This is the deeper lesson of sunglasses. Seeing better is not always seeing more light. Sometimes it is seeing less of the light that overwhelms the truth. Your eyes are not designed to welcome unlimited brightness. Vision depends on balance, contrast, and useful difference. Too much light can erase detail just as effectively as darkness can. A road washed in glare becomes less visible, not more. A lake covered in reflection hides its own depth. A snowy field under full sun can become a white emptiness where texture disappears. Sunglasses restore part of the world by subtracting from it. They take away the excess so form can return. And there is something quietly profound in that. We often imagine clarity as addition, more light, more information, more exposure, more brightness. But your eyes know a softer truth. Clarity sometimes begins when intensity is reduced. The world becomes readable when the harshest reflections are filtered, when invisible harm is blocked, when brightness no longer floods the signal. So the next time you put on sunglasses and feel your face relax, do not think of them as simple dark glass. See a filter negotiating with sunlight before it enters your body. See polarized glare being blocked, ultraviolet radiation being stopped, contrast returning to surfaces that had been drowned in shine. See your eyes receiving not less reality, but a more bearable version of it. And then let the thought settle gently. Sometimes protection is not hiding from the light, but learning which light deserves to reach you. Noise cancelling as wave destruction. Noise cancelling feels like silence being manufactured, but what your headphones are really doing is placing one wave against another so carefully that the air at your ear has less reason to move. You put them on in an airplane, a train, a busy room, or near the steady hum of an air conditioner, and the world seems to step backward. The engine does not stop, the crowd does not vanish, the fan keeps spinning. Yet inside that small space around your ears, something changes. The pressure fluctuations that would have pushed and pulled your eardrum are reduced, softened, partially erased before your brain can turn them into sound. To understand this, you first have to remember that sound is not an object flying through the air. Sound is a pattern of pressure, air molecules crowding together and spreading apart again and again, carrying vibration outward from a source. When a speaker plays a tone, it pushes air into waves. When an engine rumbles, it shakes nearby air into waves. When someone speaks, their vocal cords and mouth create changing pressure patterns that travel until they reach your ears. Your eardrum moves because the pressure outside it changes. Your brain interprets those movements as sound. Noise-cancelling headphones exploit this by making their own sound wave, not to add more noise, but to oppose the noise already coming in. If the unwanted sound is pushing air pressure upward at one instant, the headphone speaker tries to produce a matching downward pressure at the same instant. If the noise is dipping, the headphone tries to rise. When the two patterns meet at your ear, they can partly cancel. This is called destructive interference, but the phrase can be misleading if you imagine sound being destroyed everywhere. It is more precise to say that the pressure variation is reduced at a particular place. The wave from the outside and the wave from the headphone combine, and where one is high while the other is low, the result can be closer to stillness. The air still exists. Energy has not magically disappeared from the universe. The engine is still roaring outside the cup of the headphone, but at the point where your ear listens, the motion of the air can be made smaller. That smaller motion means your eardrum vibrates less, and the brain receives less noise. The silence is local. It is engineered around you like a private pocket in a moving storm. This is why active noise cancelling works best on steady, predictable, low-frequency sounds. Airplane engines, bus rumble, train vibration, ventilation systems, distant machinery. Low sounds have longer wavelengths and change more slowly, giving the electronics enough time to measure them, predict their next movement, and create an opposing wave. High, sharp, sudden sounds are harder. A clinking dish, a snapping voice consonant, a baby crying nearby, a keyboard click, a door slam. These change quickly and contain complex mixtures of frequencies. By the time the headphone detects the sound, processes it, and plays the opposite pattern, the original wave may already have shifted. Timing matters brutally. To cancel a wave, the opposing wave must arrive with the right shape at the right moment. A delay that seems impossibly tiny to you can be large enough to weaken the effect, especially for high frequencies. That is why noise-cancelling headphones also rely on passive isolation. The physical ear cups, foam tips, seals, and materials that block or absorb sound before electronics do anything. Active cancellation is the invisible strategy. Passive isolation is the physical wall. Together, they make the world quieter. Tiny microphones are the first part of the active system. Some microphones face outward, listening to the environment before the noise reaches your ear. This is often called feed-forward cancellation. It can detect outside sound early, but it has to guess how that sound will change as it passes through the headphone structure and reaches the ear. Other microphones face inward, listening inside the ear cup or ear canal area. This is called feedback cancellation. It hears what actually remains near your ear and can correct the cancellation, but it reacts after some sound has already entered the space. Many modern headphones combine both approaches, using hybrid systems that constantly adjust. Inside, a processor analyzes the incoming noise and tells the speaker what anti-noise signal to produce. That word, anti-noise, sounds dramatic, but it is simply sound-shaped to oppose another sound. The speaker is not making absence. It is making a carefully timed presence that results in less movement at your eardrum. Silence, in this case, is not nothing. It is a balance of opposites, and that is why the effect can feel almost unnatural. Your eyes still see the airplane cabin, the road, the train window shaking faintly, but your ears receive a softened version of the scene. The brain expects the visual world and the acoustic world to agree, and noise cancelling breaks that agreement. It removes part of the atmosphere from the moment. You are still inside the noise source, but not fully inside its sound. There are limits. If the headphones do not seal well, outside sound leaks in unpredictably. If your hair, glasses, jaw movement, or ear shape changes the fit, cancellation can weaken. If the noise comes from many directions with many frequencies, the system cannot perfectly oppose everything. If the sound is speech, the headphones may reduce its low parts while leaving enough of the higher detail for words to remain understandable. This is why voices often survive noise cancelling better than engine hum. Human speech is complex and rapidly changing, and your brain is very good at extracting meaning from partial signals. Even when the world is quieted, language can slip through. Some people also feel pressure or discomfort when using strong noise cancellation, even though the headphones are not usually creating actual air pressure in the way a sealed pump would. The sensation may come from the brain interpreting the unusual reduction of low-frequency sound, the seal around the ear, or slight processing artifacts. Your body is used to constant low-level noise and vibration as part of ordinary space. Remove it suddenly and the absence itself can feel like something pressing inward. This reveals an odd truth. Silence is not always neutral. Your nervous system has expectations for the background of reality. When those expectations are altered, even peace can feel strange. Noise cancelling also teaches something important about waves generally. When two waves meet, they do not crash like solid objects. They pass through each other and combine while overlapping. In one place, they may strengthen each other if their peaks line up. In another, they may weaken each other if one rises while the other falls. This is why concert halls, recording studios, car cabins and rooms have acoustic sweet spots and dead spots. Sound is shaped by reflection, timing, distance and phase. Your headphones are essentially creating a controlled interference pattern at the most important location: your ear. The goal is not to make the entire room quiet. That would require controlling the sound field across a large space, which is far more difficult. The goal is personal cancellation, a tiny zone of reduced pressure variation where perception begins. In that sense, noise cancelling is not the destruction of reality, but the editing of arrival. It does not stop the world from vibrating. It stops some of those vibrations from becoming yours. And perhaps that is why the technology feels so emotionally powerful. We live surrounded by unwanted signals: engines, vents, traffic, chatter, alarms, the endless mechanical breath of modern life. Noise cancelling gives you a rare experience of choosing what reaches you. It does not erase the world, but it proves that not every disturbance has to enter unchanged. The physics is exact, but the feeling is almost philosophical. One wave arrives with force, another meets it in opposition. The result, at least for a moment, is calm. So the next time you turn on noise cancelling and hear the room sink into softness, Do not imagine simple silence appearing from nowhere. Hear microphones listening before you do. Hear processors predicting the shape of disturbance. Hear tiny speakers creating a mirror image wave. See pressure rising and falling, meeting its opposite, leaving your eardrum less moved than it would have been. And then, let the deeper questions settle quietly. How much of peace is not the absence of waves, but the presence of something wise enough to meet them in the right shape? Why elevators change your weight? The strange thing about an elevator is that it can make your body feel heavier or lighter without changing a single atom of who you are. You step inside, the doors close, the floor hums beneath your feet, and for a moment, your body seems to lie to you. As the elevator begins to rise, you feel pressed downward, as if gravity has strengthened. As it slows near your floor, you feel strangely lighter, almost hollow in the knees, as if part of your weight has been quietly taken away. But gravity has not suddenly changed inside the elevator. Earth is still pulling you downward with almost the same strength as before. What changes is not your true gravitational weight, but your apparent weight. The force you feel from the floor pushing up against you. That upward push is what your body actually senses. When you stand still on solid ground, gravity pulls you down, and the floor pushes up with an equal supporting force. You feel that support through your feet, bones, muscles, and inner ear, and your brain interprets it as your normal weight. But an elevator does not always behave like still ground. It accelerates. It changes speed. And whenever the floor accelerates upward or downward, the support force changes with it. If the elevator starts moving upward, the floor has to do more than simply hold you against gravity. It must also push you upward fast enough to make your body accelerate with the cabin. So for a short moment, the floor presses harder against your feet. Your apparent weight increases. You feel heavier not because Earth is pulling harder, but because the floor is pushing harder. If you were standing on a scale at that moment, the number would rise, because a scale does not directly measure gravity. It measures how hard you press on it, which is the same interaction as how hard it pushes back on you. Then when the elevator moves upward at a steady speed, the feeling returns to normal. This is important. Motion itself is not what changes your apparent weight. Constant motion feels like rest if it is smooth enough. It is acceleration, the change in motion, that your body notices. The elevator can be moving upward quickly, but if its speed is constant, your apparent weight is normal again. Later, as the elevator approaches the higher floor and slows down, it accelerates downward, even though it is still moving upward. Now the floor does not need to push you as hard. Your body continues upward slightly, while the cabin reduces its upward motion, and the support beneath you becomes weaker for a moment. You feel lighter. The scale number would drop. The same pattern happens in reverse when the elevator goes down. At the beginning of a downward trip, the cabin accelerates downward, so the floor's support weakens and you feel lighter. When it slows near the lower floor, the cabin must accelerate upward to reduce its downward speed, so the floor pushes harder and you feel heavier. This is why the most noticeable sensations happen at the start and end of the ride, not usually during the smooth middle. Your body is exquisitely sensitive to changes in support. Your stomach seems to rise or sink because your organs, fluids, and tissues do not all respond at exactly the same instant to acceleration. Your inner ear, which helps sense balance and motion, contains fluid and delicate structures that shift when your motion changes, sending signals that your brain compares with what your eyes see and what your body feels. In an elevator, your eyes may see a calm box, but your inner ear feels motion, and your feet feel changing pressure. That mismatch can produce the familiar small unease, the soft drop in the stomach, the sense that the body is being adjusted by an invisible hand. This same principle appears more dramatically in roller coasters, airplanes, and spacecraft. At the top of a roller coaster hill, if the track curves downward and the seat pushes less strongly against you, you feel light or even briefly weightless. In a plane during turbulence, sudden changes in vertical acceleration can make passengers feel heavier or lighter. In orbit, astronauts are not weightless because gravity is gone. Earth's gravity is still significant even where many spacecraft orbit. They feel weightless because they and their spacecraft are falling around Earth together, so there is no floor pressing up against them in the ordinary way. Their apparent weight becomes nearly zero because the support force disappears, not because mass disappears. That distinction matters. Mass is the amount of matter and resistance to being accelerated. Weight is connected to gravity. Apparent weight is what you feel through support. In everyday language, we mix these ideas, but elevators reveal the difference with your own body. You do not need a laboratory to feel physics. You only need a moving floor. If the elevator cable were magically cut and the cabin fell freely, ignoring safety systems and air resistance for the thought experiment, you and the elevator would accelerate downward together. The floor would no longer need to support you in the normal way. You would float relative to the cabin, and a scale under your feet would read nearly zero. That would not mean you had no gravitational weight in the deeper sense. Gravity would be the reason you were falling, but because nothing would be pushing up on you, you would not feel weight. This is one of the most unsettling truths in physics. The feeling of weight is not the feeling of gravity itself. It is the feeling of being prevented from falling. When you stand on the ground, Earth pulls you downward, but the floor stops your fall, and that stopping is what becomes pressure in your feet. You feel the resistance to falling and call it weight. An elevator changes that resistance moment by moment, and your body experiences those changes as heaviness and lightness. Engineers design elevators to make these transitions smooth, because sudden acceleration would be uncomfortable and unsafe. The ride is carefully controlled, so the changes in apparent weight remain gentle. The cable, motor, counterweight, brakes, sensors, and control system all work together to move the cabin without making your body feel too much of the machinery's decisions. And yet, even in a perfectly ordinary ride, you can still feel the truth slipping through. Your body is not simply standing in a box. It is negotiating with acceleration, support, gravity, balance, and expectation. The floor is not passive. It is constantly, and expectation. The floor is not passive. It is constantly telling your body how much it must be held up. That is why an elevator can become a small philosophical machine. It teaches that what you feel most directly may not be the force you think you are feeling. You say, "I feel gravity," but much of the time you are feeling the world pushing back against gravity. You say, "I became heavier," but what changed was the pressure of support. You say, "I dropped," even when the cabin is only beginning to move. The body translates physics into sensation, and sensation turns into belief before thought can correct it. So the next time you stand in an elevator and feel that brief heaviness as it rises, or that gentle lightness as it slows, do not ignore it as a meaningless stomach flutter. See the floor pushing harder or softer beneath you. See the difference between mass, gravity, and apparent weight. See your inner ear trying to interpret motion inside a room with no moving scenery. See your body learning, for a few seconds, that weight is not just a number, but a relationship between you and whatever is holding you up. And then let the quiet question remain. How much of what you feel as heaviness in life is not the pull itself, but the pressure of being held against it? How airplanes stay lifted. An airplane stays in the sky not because it has escaped gravity, but because it has learned how to turn fast-moving air into an upward force. From the ground, flight can feel almost unreasonable. A machine weighing tens or hundreds of tons rolls down a runway, shakes, accelerates, lifts its nose, and then the wheels leave Earth as if the air has become solid enough to hold it. But the air is not solid, and the airplane is not floating like a balloon. It is being lifted by motion. Its wings are shaped and angled so that, as the plane moves forward, they interact with the surrounding air in a way that pushes air downward and creates an upward force on the aircraft. That upward force is lift. To understand it, you have to stop imagining air as empty space. Air has mass. It can be pushed, redirected, compressed, accelerated, and made to push back. When a wing moves through it, the wing does not simply slice through nothing. It meets billions of air molecules every instant and changes their motion. The wing's curved shape and its angle relative to the oncoming air help guide airflow over and under it. The air moving over the top of the wing generally speeds up and the pressure there becomes lower, while the air below the wing is often at higher pressure, especially when the wing is angled to meet the flow. That pressure difference contributes to lift, but it is not the whole story by itself. At the same time, the wing is deflecting air downward, and by pushing air downward, the airplane receives an upward reaction. These two explanations are not enemies. They are two ways of looking at the same event. The wing changes the air's motion and pressure pattern, and the result is an upward force. The common myth says wings lift because the air over the top must meet the air underneath at the back edge at the same time, so the top air has to move faster. That equal transit time idea is false. Air over the top often does move faster, but not because it is racing to reunite with the air below on a schedule. The real behavior comes from the wing shape, angle of attack, fluid flow, pressure gradients, and how air follows the surface before leaving the wing. A flat plate can produce lift if it meets the air at the right angle, and an airplane can even fly upside down if the pilot sets the angle correctly and the aircraft has enough speed and control. This alone tells you the wing's curve is helpful but not magical. Flight is not granted by one shape. It is negotiated by speed, angle, airflow, and control. During takeoff, the engines do not lift the airplane directly into the air like hands lifting a stone. Their main job is to create thrust, pulling or pushing the airplane forward fast enough for the wings to generate sufficient lift. As speed increases, more air flows over the wings each second, and the wings can redirect more air and create a stronger pressure pattern. When lift becomes greater than the airplane's weight, the plane can climb. But pilots do not simply go fast and rise. They manage angle of attack, which is the angle between the wing and the oncoming airflow. Increase this angle, and the wing can produce more lift up to a point. But beyond that point, the airflow can no longer follow the wing smoothly. It separates, becomes turbulent, and lift drops sharply. This is called a stall. A stall does not mean the engine has stopped. It means the wing has stopped producing enough smooth lift because the angle of attack is too high for the airflow to stay attached. That is why airplanes can stall at many speeds if the angle is wrong, and why pilots train so carefully to recognize and recover from it. In recovery, the key is often to reduce the angle of attack, let smooth airflow return, and regain lift. This is one of flight's most important lessons. More upward tilt is not always more safety. Push the wing too far against the air, and the invisible support collapses. Air must be invited to flow, not violently commanded beyond what it can follow. Flaps on the wing help during takeoff and landing because they change the wing's shape and increase its ability to produce lift at lower speeds. When extended, they increase curvature and often increase wing area, allowing the airplane to fly more slowly without losing lift. This matters because takeoff and landing need lower speeds for runway length, control, and safety. But flaps also create more drag, the resisting force that acts against forward motion. Drag is the price of moving through air. Some drag comes from the shape of the airplane pushing air aside. Some comes from skin friction as air rubs along surfaces. Some comes from the very production of lift itself, because creating lift changes the airflow and leaves swirling patterns behind, including wingtip vortices. These vortices form because higher pressure air below the wing tends to curl around the wingtip toward the lower pressure region above, creating rotating trails of air behind the aircraft. Large airplanes can leave strong wake turbulence, which is why planes must be spaced carefully during takeoff and landing. Even after the aircraft has passed, the air remembers it. The sky is not untouched by flight. It is stirred, twisted, and patterned by every wing moving through it. The shape of an airplane is therefore a collection of compromises. Long, slender wings can be efficient because they reduce certain kinds of drag, which is why gliders and many long-range aircraft have high-aspect wings. Shorter, stronger wings may be better for speed, maneuvering, or structural reasons. The fuselage must carry passengers or cargo, but it also creates drag. The tail surfaces help stabilize and control the airplane, giving the pilot ways to pitch, roll, and yaw. Ailerons on the wings help roll the plane. The elevator helps raise or lower the nose. The rudder helps control yaw. Flight is not just lift holding weight, It is a constant balancing act among lift, weight, thrust, and drag, guided by control surfaces that change how air moves around the aircraft. When an airplane cruises at altitude, it may feel still from inside the cabin, like a room suspended above the world. But outside, the aircraft is in a continuous exchange with the atmosphere. The engines maintain forward motion against drag. The wings maintain lift against weight. The controls make small corrections. The air changes with turbulence, temperature, density, and wind. Higher altitude air is thinner, which can reduce drag and improve efficiency. But thinner air also means the wings and engines interact with fewer air molecules. So aircraft must be designed and operated within limits. Speed, altitude, temperature, and weight all matter. A heavily loaded airplane needs more lift, which may require more speed, more runway, different flap settings, or careful performance planning. Hot air is less dense than cold air, so on a hot day or at a high-altitude airport, the airplane may need more runway to take off because the wings and engines have less dense air to work with. This is why flight is never separated from weather. The air is the runway after the runway ends. It is the medium, the support, the resistance, the invisible landscape through which the airplane must travel. And perhaps that is the deepest shift in understanding. Airplanes do not conquer the sky by ignoring the air. They fly by cooperating with it under strict rules. The wing must meet the airflow correctly. The engine must supply motion. The pilot or autopilot must keep the aircraft within safe boundaries. The structure must handle bending, vibration, pressure, and repeated loads. Every flight is a controlled relationship with an invisible substance that can hold you only if you move through it in the right way. There is something almost philosophical in that. The airplane rises not by denying gravity, but by continuously answering it. It does not defeat falling once and for all. It postpones falling through motion, design, and balance. The moment the conditions fail, the sky stops feeling like support and becomes distance again. Yet when everything works, a wing turns forward speed into upward force so smoothly that a cabin full of people can drink coffee, close their eyes, and forget they are being carried by moving air. So the next time you watch a plane lift from a runway, do not see only metal becoming airborne. See air being pushed downward. See pressure changing over a wing. See thrust buying speed, speed feeding lift, lift answering weight, and control surfaces shaping the invisible river around the aircraft. See a machine that stays up not because the sky is empty, but because the sky is full enough to push back. And then let the quiet question remain. How many impossible things become possible not by escaping the forces against them, but by learning how to move with those forces so precisely that resistance becomes support? Why tires grip roads? A tire does not grip the road by simply pressing hard against it. It grips because soft rubber is constantly being deformed, stretched, squeezed, and made to fit a rough world that looks smooth only from far away. When you look at a road, you may see a flat black surface, a strip of asphalt, a place where wheels roll and footsteps pass. But to a tire, the road is not flat at all. It is a jagged landscape of stone grains, tiny peaks, pores, cuts, ridges, dust, moisture, tar, and old scars left by traffic and weather. The tire meets this landscape through a small region called the contact patch, the only part of the tire actually touching the ground at any instant. For a car tire, that patch may be roughly the size of your hand, sometimes larger or smaller, depending on load, tire pressure, design, and conditions. It is almost unsettling to realize that an entire vehicle, with its weight, speed, braking, steering, and safety, depends moment by moment on 4 small patches of rubber meeting the road correctly. Everything the car does must pass through those patches. Acceleration, braking, cornering, stability, control, all of it is negotiated there. The tire grips because rubber is not rigid. It flows slightly into the road's microscopic texture, wrapping around tiny roughness and creating many small points of resistance. Some grip comes from adhesion, the attraction between rubber and the road surface at very close contact. Some comes from deformation, where the rubber is bent and squeezed around the road's texture, and energy is required to pull it free again. This is why tire rubber is carefully engineered. It cannot be too hard, or it will not conform enough to the road. It cannot be too soft, or it may wear quickly, overheat, feel unstable, or waste energy. A good tire is a compromise shaped by chemistry, temperature, tread design, road surface, and purpose. Racing tires, winter tires, all-season tires, off-road tires, and truck tires do not use the same rubber or patterns because they are solving different versions of the same problem. How to keep contact useful when the road is changing beneath you. On a dry road, maximum grip often comes from a large, clean area of rubber touching the surface. This is why racing slicks have no deep tread on dry tracks. They are not missing something. They are maximizing contact where water removal is not the main concern. But on ordinary roads, rain exists, dust exists, mud exists, snow exists, and the tire must do more than touch dry pavement. Tread patterns are there to manage contamination between rubber and road. In rain, grooves give water somewhere to go. Without channels, a layer of water can build under the tire, lifting it away from the road. When that happens strongly enough, the tire can hydroplane, meaning it rides on water instead of gripping pavement. Steering becomes weak or disappears. Braking becomes frightening, and the car feels as if it has been separated from the earth by a thin, moving sheet. Hydroplaning is not caused by the tire forgetting how to grip. It happens because the rubber can no longer reach the road. The water has become a temporary barrier. Tread depth, speed, water depth, tire pressure, and road texture all affect the risk. At higher speed, the tire has less time to push water aside. Worn tread has less space to channel it. Low pressure can change the shape of the contact patch in dangerous ways. The grip you trust is not guaranteed. It depends on whether the tire can maintain real contact through whatever lies between it and the road. Snow and ice change the story again. On ice, the surface offers far less texture for rubber to hold, and a thin film of water can make it even more slippery. Winter tires use compounds that stay flexible in cold weather because ordinary rubber can become too stiff when temperatures drop. They also use tread shapes and tiny cuts called sipes that create more biting edges, helping the tire interact with snow and slush. Strangely, snow can sometimes grip snow better than rubber grips ice. So winter tire patterns may hold small amounts of snow in the tread to improve traction on snowy roads. That detail feels almost contradictory until you realize that grip is always about the interface, the meeting place, not the material alone. A tire is only as good as its relationship with what it touches. Tire pressure matters because it shapes the contact patch. Too much pressure can reduce the area of contact and make the tire less able to conform to the road. Too little pressure can make the tire flex too much, heat up, wear unevenly, and respond poorly. The tire is not just a ring of rubber, it is an air-supported structure. The air inside carries much of the load, holding the tire in the right shape so the tread can meet the road as designed. Under braking or cornering, the car's weight shifts. When you brake, more load moves toward the front tires, giving them more potential grip, but also asking more from them. When you accelerate, load shifts rearward. When you turn, load shifts outward. But grip does not increase perfectly in proportion to load. A tire carrying more weight can produce more grip, but it becomes less efficient as the load rises. This is one reason balanced driving matters. Sudden movements can overload one tire while underusing another, shrinking the margin of control. Smooth steering, braking, and acceleration are not only about comfort, they help the tires stay within the range, where they can keep their grip. There is also a subtle truth about sliding. A rolling tire does not grip best when there is no microscopic slip at all. During braking and acceleration, a small amount of slip can help generate strong force. The tread elements touch the road, deform, stretch slightly, and then release as the tire rolls onward. If the wheel locks completely during braking, the tire stops rolling and skids across the surface. Once it is sliding freely, grip often drops, steering control is lost, and the tire may leave a mark as rubber is scraped away. Anti-lock braking systems help by preventing full lockup. Rapidly adjusting brake pressure so the tires remain closer to the useful gripping range where they can still steer and slow the car. The goal is not mystical. It is to keep the tire from crossing from controlled deformation into uncontrolled sliding. Temperature plays its own role. Rubber compounds have operating ranges. Too cold, and they may not conform or chemically interact as well. Too hot, and they can become greasy, wear rapidly, or lose structure. Racing drivers warm tires because grip depends on the rubber being in the right state. Everyday drivers experience this more quietly when cold mornings make tires feel harder, or when long, fast driving changes pressure as the air inside warms. Road surface also matters. Fresh asphalt, polished concrete, gravel, painted lines, metal bridge joints, wet leaves, oil patches, and loose sand all present different challenges. A tire can only grip what the surface allows. This is why the same car can feel secure on one road and nervous on another. The vehicle did not change. The conversation under the tire changed. And perhaps that is the deeper lesson hidden in tire grip. Control is not something the car owns by itself. It is borrowed from contact. It exists only while the tire, road speed, load, pressure, temperature, and driver inputs remain in a workable balance. The moment that balance fails, the illusion of certainty disappears. So the next time you see a car take a curve, stop at a light, or move quietly through rain, do not see only wheels turning. See small contact patches carrying enormous responsibility. See rubber bending into rough stone. See grooves evacuating water. Air pressure shaping the tread. Temperature softening or stiffening the compound. And the road offering or refusing grip. See safety as a relationship renewed every fraction of a second. And then let the thoughts settle gently. Sometimes what keeps you moving through the world is not power, not speed, not confidence, but the fragile honesty of contact with the ground beneath you. Why dust floats in sunlight? Dust does not suddenly appear when sunlight enters a room. The beam only exposes the invisible traffic that was already drifting through your air. You open a curtain in the morning, and a bright shaft of light cuts across the room like a quiet stage lamp. Inside it, tiny specks float, swirl, rise, fall, vanish, and return, moving with a strange patience, as if the air has become a slow river full of miniature stars. It can feel almost unreal because the room seemed clean a moment before. Nothing looked suspended. Nothing seemed to be moving. But the sunlight reveals what ordinary lighting hides. The air around you is never empty. It carries fragments of skin, fibers from clothing, bits of paper, pollen, soot, soil, tiny mineral grains, dried droplets, and microscopic debris produced by ordinary living. Most of these particles are too small to notice under normal conditions, not because they are absent, but because they do not send enough light into your eyes to stand out from the background. Sunlight changes that. When a narrow beam enters through a window, it creates a bright path against darker surroundings. Dust particles inside that path scatter the light. They catch a portion of the incoming sunlight and redirect it in many directions, including toward your eyes. That scattering is why the particles become visible. The dust is not glowing from within. It is borrowing the sun's light for a moment and throwing a tiny piece of it back to you. The darker the background and the stronger the beam, the more dramatic the effect becomes. This is why dust looks magical in a sunbeam, but disappears when the whole room is evenly lit. Visibility depends not only on what exists, but on contrast. The world can be full of motion, and yet you see nothing until the lighting gives motion an outline. But why does the dust float instead of simply falling straight to the floor? The answer begins with size. Dust particles are extremely small, and small things do not move through air the way stones move through empty space. A large object falls because gravity pulls it down strongly compared with the resistance of the air. But a tiny particle has very little mass, so the pull of gravity on it is weak, while the drag from air is relatively important. As it falls, the air pushes back against it, and very quickly it reaches a slow settling speed. Some particles fall so slowly that the faintest air movement can keep them suspended for long periods. A door opening, a person walking, warm air rising from a radiator, your own breathing, heat from sunlight on the floor, or airflow from a vent can carry dust upward or sideways before it ever reaches the ground. The room may look still to you, but it is not still to dust. To a speck of dust, the air is not an empty backdrop. It is a moving landscape, full of currents, eddies, and invisible slopes. Warm air tends to rise because it is less dense than cooler air around it. And this slow rising motion can lift dust. Cooler air can sink. Obstacles like furniture, curtains, walls, and your body shape the flow into soft swirls. That is why dust in sunlight seems to dance. It is not alive. It is being carried by air currents too gentle for your skin to feel. In a way, dust reveals the weather inside a room. Every floating speck becomes a tracer, showing you the hidden motion of the air you breathe. There is also a more delicate kind of motion at small scales. Very tiny particles can be jostled by collisions with air molecules. The air molecules themselves are moving rapidly in all directions, even though you do not see them, and their uneven impacts can make small particles tremble and wander in a jittery way. This is called Brownian motion. For larger dust grains, room air currents dominate, but for the tiniest particles, molecular nudges become part of the story. The stillness of the room is only a human illusion. At smaller scales, everything is restless. Air molecules collide, particles drift, light scatters, heat creates circulation, and gravity patiently pulls downward. The dust you see is caught between all of these influences. Some particles settle onto shelves, screens, books, and floors. Others are stirred back up by movement. Cleaning removes what has landed, but walking, wiping, sweeping, or changing fabrics can also send some particles back into the air. Even a bed, a carpet, or a sofa can become a reservoir of dust that releases small amounts when disturbed. This does not mean you should be afraid of every sunbeam. It means the indoor world is more dynamic than it looks. Your room is not a sealed, frozen container. It is an exchange system. Air enters and leaves. Surfaces shed and collect. Humans breathe, move, and shed cells. Fabrics release fibers. Outdoor particles come in through windows, shoes, clothing, and ventilation. The dust in sunlight is a record of contact between your body, your home, and the outside world. It is matter that has been separated from larger things and made light enough to travel. Some particles are harmless in normal amounts. Others, like smoke, mold spores, fine pollution, or allergens, can matter for health depending on concentration, sensitivity, and exposure. This is why filtration, ventilation, humidity control, and regular cleaning can improve indoor air quality. A good filter can trap many particles by forcing air through fine fibers where particles collide, stick, or become caught. Ventilation can dilute indoor particles by replacing some indoor air with outdoor air, though outdoor air itself may carry pollution or pollen. Humidity also changes behavior. Very dry air can let some particles remain light and easily disturbed, while higher humidity can make some particles clump or settle differently. Though too much humidity can encourage mold, the air in a home is a balance, not a blank space, and sunlight makes that balance visible for a few minutes. The beam shows you that seeing is often selective. Dust outside the beam still exists, but it blends into the room because light is not revealing it with the same contrast. This is similar to standing in a theatre where only one actor is under the spotlight. The rest of the stage has not disappeared. It has simply fallen below your attention. The sunbeam is a spotlight for suspended matter. It teaches that invisibility is not the same as absence. There are particles around you right now that you cannot see, currents you cannot feel, collisions you cannot hear, and slow settling processes that continue whether you notice them or not. The room is constantly becoming itself, losing pieces, gathering pieces, breathing in, breathing out. And there is something quietly humbling in that. Dust is often treated as failure, as proof that a place has been neglected. But scientifically, it is also evidence of life and time. A perfectly unused, untouched, airless room would gather dust differently. Your dust contains the story of movement, doors opened, clothes worn, skin renewed, pages turned, windows cracked, meals cooked, outside air entering, seasons changing. The specks in sunlight are not merely dirt. They are fragments of a lived environment, made visible by geometry, light, and air. So the next time you see dust floating in a sunbeam, do not rush to see only mess. See sunlight scattering from tiny travelers. See particles falling so slowly that air currents can rewrite their path. See warm and cool air drawing invisible loops through the room. See a private weather system revealed by a golden line from the window, and then let the thoughts settle softly. Sometimes the world does not become more magical when something new appears, but when light finally shows you what had been moving around you all along. Why knives cut? A knife does not cut because it is powerful. It cuts because it makes a small amount of force arrive at an almost impossibly small place. Hold a dull spoon against a tomato and press, and the skin resists, stretches, bruises, and collapses before it opens. Hold a sharp knife against the same tomato, and the surface parts with almost disturbing ease, as if the blade has whispered the correct instruction to the material. But the knife is not casting a spell. It is concentrating pressure. Your hand may apply only a modest push, but the edge of the blade narrows that push into a thin line, so the force is no longer spread across a wide area. It is focused into a tiny region where the material can no longer hold itself together. This is the first secret of cutting. It is not about overwhelming the whole object. It is about exceeding the strength of one narrow path through it. The blade edge acts like a controlled beginning of failure. It chooses where the material should separate. Without the edge, force spreads out and the object may bend, dent, or resist. With the edge, the same force becomes decisive. A sharp knife is not merely thinner at the edge. It is a tool for directing damage with precision. When it enters bread, fruit, meat, paper, rope, or wood, it creates a highly concentrated stress at the point of contact. And once the material starts to split, the sloped sides of the blade help push the two sides apart. This is why a knife is also a wedge. The edge begins the separation, and the wider body of the blade continues it, opening the cut as the knife advances. You can feel this difference when slicing compared with pressing straight down. If you simply push a blade downward, the material must fail all at once along the edge. But when you draw the knife forward or backward, the edge moves across the surface gradually, attacking a smaller region at each moment. Slicing reduces the force needed because the blade is not asking the entire cut to happen at once. It is turning one big act of separation into many tiny acts of separation, arranged in a line. This is why a chef's knife glides when used with a steady slicing motion, and why even a sharp blade can feel clumsy if you only crush downward. Serrated knives reveal another layer of the story. Their edges are not smooth lines. They contain small points and valleys, like tiny teeth. Those points concentrate force even more strongly at specific spots, letting the knife bite into tough outer surfaces such as bread crust or tomato skin. Once the teeth catch, the sawing motion tears and parts the material bit by bit. A serrated blade may not create as clean a cut as a finely sharpened smooth blade, but it excels when the surface is tough and the inside is soft, because it can grip instead of sliding. This is why bread knives work so well. The crust resists a smooth push, but serrations grab and fracture it without crushing the airy structure inside. The kind of material being cut matters just as much as the blade. A carrot cracks and splits differently from a tomato. Bread compresses. Meat fibers separate along tissues. Paper tears through a network of cellulose fibers. Rope cuts as many twisted strands are severed one by one. Wood resists according to grain direction. Skin and plant surfaces may stretch before they rupture. Every material has its own hidden architecture, and a knife succeeds by exploiting that architecture. Cutting is not one universal action. It is a conversation between edge shape, blade angle, motion, force, and the internal structure of what is being cut. A very sharp blade can slice cleanly because it creates a narrow, controlled separation with less crushing around it. A dull blade, by contrast, has a rounded or damaged edge. Under magnification, even a knife that looks smooth may have bends, chips, flattened regions, and microscopic irregularities. When that edge becomes too rounded, it cannot concentrate force as effectively. It presses and drags rather than enters. You instinctively compensate by pushing harder, but that extra force makes the cut less controlled and can make the blade slip. That is why a sharp knife is often safer than a dull one when used properly. The sharp knife requires less force and gives more predictable control, while the dull knife tempts your hand into violence. Sharpening restores the geometry of the edge. Honing, which is often done with a steel rod, does not always remove much material. Instead, it can realign a slightly bent edge so it meets the material cleanly again. Actual sharpening removes metal to create a new edge. This matters because cutting ability is partly about angle. A very narrow edge can be extremely sharp, but if the metal is too soft or the angle too delicate for the task, it may bend, chip, or wear quickly. A heavier chopping blade may use a wider, tougher edge because it must survive impact. A razor can be made extremely thin because it cuts softer material and is not meant to strike bone, wood, or hard surfaces. Blade design is always a compromise between sharpness, durability, ease of sharpening, and purpose. Steel itself carries another hidden story. Good knife steel must be hard enough to hold an edge, but not so brittle that it breaks easily. Heat treatment changes the internal structure of the metal, helping determine whether the blade becomes tough, hard, flexible, or fragile. This is why two knives that look similar can behave very differently. One may lose its edge quickly, another may stay sharp but chip if misused. Another may sharpen easily but require frequent care. The cut you see in the kitchen is the final expression of metallurgy, geometry, hand motion, and the structure of food. Even the cutting board matters. A board that is too hard, like glass or stone, can damage the edge by forcing the fine blade tip to deform or chip on impact. Wood and certain plastics are gentler because they give slightly under the blade, preserving the edge longer. So the act of cutting is never just blade against object. It is blade, hand, surface, material, and motion forming a temporary system. And the more carefully you look, the more a knife becomes a philosophical object. It teaches that separation does not always come from brute strength. Sometimes it comes from focus. A blunt force tries to move everything at once and often creates bruising, crushing, and waste. A sharp edge asks for one narrow opening and follows it with discipline. It does not fight the whole material. It finds the line where the material can begin to yield. That is why cutting can feel so clean, almost silent when everything is right. The blade enters at the proper angle. The hand guides rather than attacks. The material opens along the path of least resistance, and what looked whole becomes two parts, not through chaos, but through directed pressure. So the next time you slice an apple, sharpen a blade, or watch a knife pass cleanly through paper, do not see only a simple tool doing a simple job. See force concentrated into geometry. See a wedge turning pressure into separation. See microscopic edges, fibers, grains, skins, cells, and structures being asked to release along a chosen line. And then, let the quiet question remain. How much of the world changes, not because more force is used, but because the force finally becomes focused enough to matter? How pressure cookers work. A pressure cooker is not a pot that cooks with more heat. It is a sealed chamber that traps steam until water itself is forced to behave at a higher temperature than it normally would. You place beans, rice, meat, or vegetables inside, add liquid, lock the lid, and suddenly the kitchen contains a small controlled atmosphere with rules different from the open air. In an ordinary uncovered pot, steam escapes freely, carrying energy away as soon as water reaches its usual boiling point. The liquid cannot easily climb far beyond that point, because extra energy mostly goes into turning more water into vapor and sending it into the room. But a pressure cooker changes the boundary. It does not let the steam leave so easily. As the liquid heats, some water becomes vapor, and that vapor fills the space above the food. Because the lid is sealed, the vapor cannot expand into the kitchen, so pressure builds inside the pot. This higher pressure pushes back on the liquid water, making it harder for more molecules to escape into vapor. As a result, the water can reach a higher temperature before boiling vigorously under those new conditions. That is the central secret. Pressure raises the cooking temperature of the water and steam inside the sealed vessel. The food is not cooked faster because pressure itself magically softens it. It cooks faster because the trapped environment can become hotter than an open pot while still staying wet. This matters because many transformations in food depend strongly on temperature. Tough fibers soften more quickly. Starches absorb water and swell. Beans become tender as their cell walls and internal structures break down. Collagen in tough cuts of meat can convert into gelatin, giving stews and broths that rich softness people associate with long cooking. In a normal pot, reaching those changes may take hours because the food is limited by the temperature of boiling water at that pressure. In a pressure cooker, the same moist environment can work at a higher temperature, so the chemical and physical changes happen faster. It is like asking time to move through warmer water, but the pressure cooker is also misunderstood. It does not make food dry like an oven, and it does not brown food well once sealed, because browning reactions need relatively dry, hot surfaces. Inside the cooker, the environment is humid and filled with steam, so it is excellent for moist cooking, tenderizing, and heat transfer, but not naturally good at crisping. That is why many recipes begin by browning onions or meat with the lid off, then sealing the cooker afterward. The browning builds flavor first. The pressure phase then drives tenderness and speed. Once sealed, the steam becomes more than a byproduct. It becomes part of the cooking system. Steam carries heat efficiently, condenses on cooler food surfaces, gives up energy, and helps the food warm quickly and evenly. The liquid at the bottom provides moisture and prevents the cooker from running dry. Without enough liquid, the system cannot make enough steam. Heat distribution becomes dangerous, and food may scorch. The pressure cooker needs water not just as an ingredient, but as the working fluid of the machine. It is the messenger carrying energy through the sealed space. Modern pressure cookers also depend on safety engineering because trapped pressure is powerful. The lid locks so it cannot be opened while pressure remains high. A rubber or silicone gasket helps make the seal. A valve or pressure regulator releases excess steam to keep the pressure within a designed range. Many cookers have backup safety systems in case the main vent becomes blocked. This is why keeping the valve clean matters. A pressure cooker is safe when used correctly, but it deserves respect because it stores energy in compressed steam and hot liquid. The danger in old stories often came from clogged vents, damaged seals, overfilling, or opening the cooker before pressure dropped. Modern designs are much safer, but the physics has not become gentle. It has only been controlled. Overfilling is especially important because foaming foods like beans, grains, or lentils can block the vent if there is not enough empty space above them. That empty space is not wasted volume. It is the breathing room of the pressure system. When cooking ends, pressure must be released carefully. A quick release opens a path for steam to escape rapidly, dropping pressure fast. This is useful for foods that overcook easily, but it can cause foaming or splattering with starchy or fatty liquids. A natural release lets the cooker cool and pressure fall more gradually, which can be better for soups, beans, meats, and foods that benefit from resting. During natural release, cooking continues for a while because the interior remains hot. The flame or heating element may be off, but the sealed system is still carrying stored heat. This is why timing in pressure cooking includes more than the minutes at pressure. The food experiences heating up, pressurized cooking, and cooling down. All three stages matter. Electric pressure cookers make this feel automatic, but the same physical story is happening inside. Heat enters, steam forms, pressure rises, sensors or regulators control the process. Food cooks in a hot and moist environment, and then pressure falls. At high altitudes, where outside air pressure is lower, ordinary boiling happens at a lower temperature, making cooking slower. A pressure cooker is especially useful there because it creates its own higher pressure environment, partly restoring the higher cooking temperatures that open pots lose in thin air. This reveals the deeper role of pressure. It is not just force, it is permission for water to carry heat at a different level. The pressure cooker works by changing what boiling means inside a sealed world, and there is something quietly profound in that. The same ingredients, the same water, the same kitchen, the same stove can produce a different outcome when the boundary changes. Leave the pot open and steam escapes. Seal the pot, and the escaping vapor becomes pressure. Pressure changes temperature. Temperature changes time. Time changes texture. Texture changes the meal. Nothing supernatural has been added. The system has simply been closed. and by closing it, energy that would have fled into the room is made to remain and work. So the next time you hear a pressure cooker hiss softly on the counter, do not hear only a kitchen appliance. Hear water negotiating with confinement. See steam gathering in a sealed space. Pressure raising the point where liquid can remain hot. Valves guarding the limit. And food transforming faster because the environment around it has been rewritten. And then, let the ordinary machine leave you with a quiet question. How many things in life change not because more force is added, but because what once escaped is finally held long enough to become useful? Why popcorn explodes. A popcorn kernel is a tiny pressure vessel disguised as food, waiting for heat to turn the water hidden inside it into the force that tears it open. Before it pops, it looks almost lifeless. A hard golden seed, dry to the touch, too small to suggest violence, too ordinary to suggest architecture. But every popcorn kernel is built like a sealed machine. Its outer shell, called the pericarp, is unusually tough and moisture-resistant compared with many other grains. That shell is the reason popcorn is popcorn. It holds the inside together long enough for pressure to build instead of letting moisture escape too early. Inside the kernel is starch, a small amount of water, proteins, and other seed material arranged for the life of a plant, not for your snack bowl. Yet when you heat it, that biological design becomes a physical trap. The water inside the kernel begins to warm. As temperature rises, some of that water becomes vapor. But because the shell holds it in, the vapor cannot freely leave. Pressure climbs inside the kernel. At the same time, the starch granules inside are heating, softening, and becoming more gel-like as water and heat change their structure. The kernel is now in a strange state. The outside remains hard and sealed, while the inside becomes hot, pressurized, and increasingly unstable. This is why popcorn does not simply crack open slowly like a drying seed. It waits until the internal pressure and temperature reach a breaking point. Then the shell fails suddenly. In that instant, the pressure inside drops extremely fast. The superheated water flashes into vapor, expanding violently, and the softened starch is forced outward. What was once compact and hidden turns inside out into a white foam-like structure that freezes into shape as it cools. The fluffy popcorn you eat is not the kernel's original inside gently unfolding. It is expanded starch, blasted outward and set into a new form by a sudden release of pressure. The pop is not a chemical explosion like gunpowder. It is a physical explosion, a rapid rupture caused by heated water, trapped pressure, and a shell strong enough to delay release until the change becomes dramatic. This is why not every grain of corn can pop properly. Ordinary corn may dry, crack, burn, or split, but it does not have the same combination of hard outer shell, dense, starchy interior, and internal moisture balance that popcorn varieties have. The kernel needs enough water to create pressure, but not too much. It also needs the shell to remain intact, long enough for that pressure to rise. If popcorn is too old or too dry, many kernels become old maids, the unpopped ones at the bottom of the bowl. They may have lost too much moisture through tiny leaks in the shell, so heating them cannot generate enough internal pressure. If the shell is cracked, pressure escapes early. If the heat is too low or uneven, moisture may leak away before the kernel reaches the right conditions. If the heat is too intense, the outside may scorch before the inside transforms properly. A good pop is a timing event. The kernel must be heated quickly enough and evenly enough that the interior reaches its explosive threshold before the system fails in a weaker, quieter way. This is why oil can help on a stovetop. Oil spreads heat efficiently across the kernel surface and allows many kernels to heat more evenly, reducing scorching and giving the internal water a better chance to build pressure. In hot air poppers, moving hot air performs the heating without oil, but the principle remains the same. The kernel must be driven toward that sudden moment of rupture. The shape of popped corn also tells a hidden story. Some popcorn becomes irregular and winged, often called butterfly-style popcorn, with delicate branches that catch butter and seasoning. Other popcorn pops into rounder, denser mushroom shapes, often preferred for caramel corn because they are less fragile and coat more evenly. These shapes depend on the kernel variety, starch structure, moisture distribution, and how the shell breaks. The final piece of popcorn is a frozen record of how the kernel failed. A small crack begins. Pressure escapes through it. Starch expands through the opening, and the whole seed flips itself into a new architecture in a fraction of a second. The sound you hear is the shell breaking and the rapid expansion disturbing the air. It is a tiny acoustic signature of stored pressure becoming motion. And the transformation is enormous compared with the kernel's original size. A hard seed becomes a light, porous structure because the inside has been inflated like edible foam. That foam is mostly starch, but it is full of air pockets and thin walls, which is why popcorn feels crisp and fragile instead of dense. When it absorbs moisture from the air, it can become chewy or stale because water softens the delicate starch structure. Fresh popcorn feels crisp because those thin walls break cleanly under your teeth. Stale popcorn has absorbed enough moisture to lose that brittle snap. Even after the pop, water continues to shape the experience. The kernel's hidden moisture creates the explosion. The air's moisture later steals the crunch. There is something quietly profound in this. Popcorn teaches that small things can hold enormous change if they have the right boundary. Without the shell, the water would escape gently. Without the water, the shell would only heat and harden or burn. Without the starch, there would be no white cloud of structure waiting to expand. The miracle is not in one part, but in the arrangement. A sealed coat, a little water, a transformable interior, and heat arriving at the right pace. It is pressure delayed until delay can no longer survive. It is ordinary matter becoming dramatic because it was held in tension just long enough. And perhaps that is why popcorn feels so satisfying beyond taste. Each pop is a miniature release, a sudden announcement that something hidden has crossed its threshold. The bowl fills with the evidence of tiny failures that became abundance. What breaks does not always become useless. Sometimes breaking is exactly what allows the hidden structure to appear. So the next time you hear kernels rattling in a pot or bursting inside a microwave bag, do not hear only a snack being made. Hear moisture trapped inside a living seed. See starch softening in the dark. See pressure rising behind a shell too strong to open early and too weak to hold forever. See a small golden body turn itself inside out and become light. And then, let the quiet question rise with the steam from the bowl. How many transformations in life are not gentle openings, but sudden releases from pressure that had been building invisibly all along? Everyday objects as physics machines. The objects around you are not passive things waiting to be used. They are small physics machines, quietly converting forces, guiding motion, storing energy, filtering the world, and shaping your body's choices before you even notice. A chair is not just a place to sit. It is a structure that takes the weight of your body, spreads it through legs, joints, screws, fibers, metal, plastic, or wood, and redirects that load into the floor without collapsing. A door handle is not just a handle. It is a lever that turns a small motion of your wrist into enough torque to retract a latch hidden inside the door. A zipper is not just a line of teeth. It is a moving alignment system, where one slider forces two rows of shaped pieces to interlock in sequence, turning loose fabric into a sealed boundary. A pencil is not just wood and graphite. It is a controlled abrasion device, leaving behind tiny layers of dark, carbon-rich material because the paper's rough fibers pull particles from the pencil tip as your hand moves. A spoon is not just a curved piece of metal. It is a shaped surface that holds liquid through geometry and lets you carry something that would otherwise flow away. Once you begin to see this, the room changes. The ordinary world stops looking like a collection of objects and starts looking like a museum of invisible engineering. Every object is asking and answering a question. How can force be redirected? How can weight be supported? How can motion be slowed, stored, repeated, or controlled? How can a soft human body interact with a hard physical world without tearing, slipping, burning, dropping, wasting, or breaking? A button solves one version of that question by passing through a hole and resisting backward motion because of its shape. A screw solves another by turning rotation into forward movement. Biting into material through a spiral ridge that lets your hand apply force gradually instead of all at once. A hinge solves another by allowing rotation around one controlled line while preventing motion in other directions. A spring solves another by deforming when loaded and returning when released, storing mechanical energy for a moment and giving it back. A backpack strap solves another by spreading weight across your shoulders, so pressure is not concentrated painfully in one small place. Even a simple cup is a physics machine. Its walls contain liquid, its base resists tipping, its handle separates your fingers from heat, its rim controls flow toward your mouth, and its material must survive temperature changes, cleaning, impact, and repeated use. You call it a cup because language hides the machinery. Physics sees a container, insulator, lever, heat pathway, balance system, and human interface device all at once. The same is true of a staircase. It is a machine made of stillness. It breaks one large vertical climb into many smaller rises, letting your muscles lift your body in manageable steps, instead of forcing a single impossible jump. A ramp does something similar, trading distance for gentleness, allowing wheels, carts, and bodies to rise with less abrupt force. A blanket is a thermal machine, not because it creates heat, but because it slows the loss of the heat your body already produces, trapping air in fibers and reducing the speed at which warmth escapes. A window is an optical and thermal compromise. It lets light through while trying to slow weather, dust, insects, and heat exchange. A lock is an information machine made physical, allowing the right shape or code to create motion while rejecting the wrong one. A clock is a rhythm machine, turning steady oscillations into measured time, making the invisible passage of change visible through hands, digits, or pulses. These things feel simple only because they work so well that their complexity disappears. That is one of the quiet marks of good design. When physics has been arranged so carefully that the user feels only ease. But ease is not emptiness. Ease is hidden labor. The world is full of materials chosen for their behavior. Glass is used where transparency and hardness matter, but it can be brittle. Rubber is used where flexibility and grip matter, but it can age, crack, or soften. Metal is used where strength and conductivity matter, but it can corrode, bend, or become too hot to touch. Wood is used where stiffness, warmth, and workability matter, but it swells, dries, splits, and remembers the direction of its grain. Plastic is used where lightness, shaping, and insulation matter, but different plastics behave so differently that one may bend, another may shatter, another may resist glue, another may soften in heat. Every object is a compromise frozen into form. A fork must be sharp enough to pierce food, but not so sharp that it injures your mouth. A shoe sole must be soft enough to cushion impact, but strong enough to survive the ground. A lid must seal enough to protect what is inside, but open without requiring destructive force. A mattress must yield to your body, but support it so deeply that your spine does not spend the night fighting gravity. The more you notice, the more you understand that human life is not lived directly against raw nature. It is lived through a layer of designed physics. Handles extend your grip, wheels reduce dragging, containers tame liquids, walls manage weather, lenses bend vision, filters separate what you want from what you do not. Tools let your small body act with more precision than muscle alone could offer. A hammer concentrates momentum into a nail. Scissors turn, squeezing into two crossing edges. A pulley changes the direction of a pull. A pen meters ink through a tiny controlled point. A comb organizes fibers by spacing teeth at regular intervals. A toothbrush uses thousands of small bristles to reach textures your finger cannot clean. Even a towel hook, a drawer slide, a curtain, a bottle cap, a stapler, a key, a broom, a chair wheel, a shoelace, a paperclip, and a switch are all small answers to physical problems. They manage contact, motion, storage, release, alignment, tension, friction, elasticity, balance, and flow. The machine does not need a motor to be a machine. A machine is any arrangement that transforms an input into a useful output. Your hand pushes, the object redirects. Your body leans, the structure supports. Your fingers twist, the cap seals. Your foot presses, the pedal transmits motion. Your eye looks, the lens organizes light. Your breath enters fabric, the mask filters particles. Your weight meets the floor, the sole cushions and grips. Everywhere, objects translate you into the world and translate the world back into something your body can handle. And this should make ordinary life feel less ordinary. You are surrounded by silent collaborations between matter and intention. Someone, somewhere, learned how a material bends, how a surface wears, how a joint fails, how a shape guides force, how heat moves, how pressure builds, how light travels, how fluids leak, how human fingers actually move, how tired hands behave, how impatient people pull, twist, drop, and misuse things. Every reliable object contains lessons from failure. Chairs have collapsed, handles have snapped, lids have leaked, hinges have squeaked, shoes have slipped, wires have overheated, jars have refused to open, and designs have changed because the physical world corrected human imagination. Engineering is often humility made practical. It is the admission that matter will not obey wishes unless form, force, and material are arranged properly. And perhaps that is the deeper teaching of everyday objects as physics machines. The world is not divided into magical technology and boring matter. Everything that works is technology at some scale. A woven basket is technology. A clay bowl is technology. A needle is technology. A folded paper airplane is technology. A knot is technology. The difference between ancient tools and modern devices is not that one has physics and the other does not. Both are arrangements of physical rules. One may use stone, fiber, wood, and hand pressure. Another may use circuits, sensors, magnets, and software. But both are ways of negotiating with reality. Both say, here is a problem the body cannot solve alone, so let matter be shaped into an assistant. That is why learning the physics of ordinary objects can change how you see yourself. You begin to realize that intelligence is not only inside the brain. Some of it has been placed into the environment. The shape of a handle remembers the hand. The height of a step remembers the leg. The curve of a spoon remembers the mouth. The thickness of a glove remembers heat and cold. The click of a switch remembers the need for certainty. Objects are not conscious, but they carry human understanding inside their shapes. They are thoughts turned into matter. So the next time you walk through your home, do not pass through it as if it is merely background. See the chair holding force in its frame. See the hinge allowing one kind of motion while forbidding others. See the screw turning rotation into grip. See the blanket slowing heat. The cup controlling flow. The zipper organizing separation into closure. The pencil leaving matter behind as meaning. See a world of quiet machines, each one making life slightly more possible. And then let the final thought settle softly. The universe does not become less mysterious when you understand everyday things. It becomes more intimate, because you realize the laws that move stars and storms are also hiding in the spoon. The shoe, the handle, the page, and the small familiar objects waiting patiently within reach of your hand.